Hi, Jordy. Can you hear us?
Loud and clear.
Excellent. We're not sharing here, so you are welcome to take over the share anytime you like. No one's in the room yet, so I imagine we're going to be starting a few minutes late.
Okay.
Well,
Let me know when you're all ready, and I'm all set here to start sharing.
okay, absolutely. Your chair will come up when when we're all situated here.
Great. Thank you.
Everything's good, Kevin. So if I could just plug my laptop in, then when the time's right, is that
So
okay?
you can't have your. So well, maybe just plug it
I
in.
don't want to mess anything up.
So I don't think we plan to plug it in.
Okay.
Would it be possible for you to connect to the Zoom and then like share
Yes,
remotely?
definitely.
So I think that's really the best way. If we're not going to have it on the podium computer, then just connect to the Zoom yourself and have it up here.
Yeah,
And just like the remote speakers are doing,
Yeah.
you'll just be here with a
Yeah.
microphone.
Okay.
Okay, if that's good for you,
That's
then
totally
that's good
fine.
enough for
Yeah,
us. So
definitely.
we'll just clear space for you to
Yeah.
come up here, and I think that's
Thank you.
good.
Yeah, very cool. Never cry. Sorry, never cry. I think that I don't know what you're using to ask that.
You got your work set up.
Yeah, so I just attached this together. Self-explanatory.
And I think the way a lot of the challenges it's just letting it run for questions or let it run to me for 3 minutes.
Yeah.
One year, one state. But the main thing is like.
On Zoom, just. Yes.
Just
Are there questions?
no one's asked for it. I'm keeping an eye on it, but 0 people have asked.
Great.
And it's more difficult on YouTube because they're on like about a minute lag. So if they had a question,
It's not.
we might be able to catch it.
Yeah,
It's only
okay,
about-
okay, it would just be like typing it.
It just, yeah, maybe you can actually.
No. It's kind of slightly, is that slightly gonna revisit it? Or is this wasteful?
It is. So
We're still on the bed.
probably not.
Maybe I should go and read it.
Yeah, I mean, it's never the face. It's actually obviously just it's the jade image is absurd, but actually it's not that. So I don't say so. Yeah, 28. It's definitely still second, but it's not a face. So, what would you mean to do or?
No, well, one, that'd be great, but it's probably not all very.
Yeah, I'm just wondering, like, just to see.
You know, to see that, to get another multi-band. Metric. See that it's in a
It's this observation, like this last observation was Jane. So, and I think the observing window is basically the earliest.
I'm just gonna check to make sure that people are in motion.
October. So you yes, because
right after this.
or like, um, but let's say yours. Seven Or I also wasn't sure like what is the space of the spine? So this is so it is about, so it's gonna be at earliest. Yeah.
We went and you told everyone that they were ready to start, but yeah, they were all just eating outside, so. Yeah. Basically has an extra required, that way it's great, that we have to have it in the gym, it's okay. Yeah. No, I told them, please, okay, please come in because we're ready to start. Yeah, because I'm not the fun here.
This is like, probably, I mean, it's fun. This, two very individual on.
Is this on? All right, we're gonna get started while people are trickling in because we're already running a couple minutes behind. But this session is the first of two sessions on black holes and accretion. My name is Sylvia Biscavani. I'm going to be the chair. And we have 4 talks. So we're going to start with a talk on Zoom from Jordi Davilo. So Jordi, whenever you're ready, you can take it away.
Thank you, Sylvia. Let's see. This should be on the screen by now. Great. Yeah, so hi everyone, I'm Jordi Davelaar. I just started as an Einstein Fellow at Princeton University, and unfortunately not in Pasadena. I'm actually 9 hours ahead of you all. It's almost midnight here in Europe. And today I would like to give a short overview on the things I worked on previously and highlight some of the things that I hope to start working on now as a Hubble Fellow. And all of this work will revolve around massive black hole binaries. So let's take a step back. What are massive black hole binaries? Well, we expect them to be numerous in the universe. We expect them that they were formed in galactic mergers. So as the galaxies bring in a black hole of their own, these black holes will interact with the stars and the gas that is in these galaxies or the newly formed galaxy, and they will sink towards each other, eventually ending up in the gravitational wave band of PTA and LISA. But these gravitational wave detectors are not very good at sky localization. So for this, we rely on electromagnetic signatures, but this is where the catch is. We don't really have a clear telltale signature to look for if we want to figure out what galaxy exactly produced the gravitational wave or which is harboring this black hole binary. And this is important because we want to understand where these black hole binaries are formed as a function of redshift, how these galaxies are affected by their black hole binary occupation. For example, are they quasars, are they non-quasars, are they radio loud or not? And in that way, we can understand how they evolve and shape the galaxies they're in. Luckily for us, in contrast to LIGO, these black holes do not have a vacuum around them. They actually have a quite gaseous environment, also when they get closer and closer towards their in-spiraling phase, because these binary systems are surrounded by what we call a circumbinary disk, which is shown here in this cartoon in the red. And then in the center, you have 2 black holes here, which are rotating around each other. And as they rotate, they strip mass from the inner radius of the circumbinary disk and transfer that material to their own mini disks. These are shown here in blue. So that's like the overall picture you need to have in mind, which is very different from either a single black hole or stellar mass binary black hole system. So what kind of observational evidence can these systems then produce? Well, the most naive way to look at this is to think about, okay, if you have two orbiting systems and they actually have gas around them and this gas can emit, well, maybe like a Doppler modulated signature could be of like a nice first try to figure out if a certain AGN or quasar is an actual black hole binary. And this is like what the current state of the art, like most people look for these things in like large time domain surveys, and we're getting close to like 200 candidates. They typically have like a high mass, like 10 to the 9 solar masses, orbits of roughly a year, because like these time domain surveys bias us towards like the higher mass end of the mass function, and also to larger orbits because of their time cadence. But there's a big catch here. Like these periodical-like signatures, an example here shown on the right side of the screen, you have this data which like nicely sort of follows like this periodic behavior. Like you only get like one, maybe 1.5, maybe 2 orbits, and given that you don't have a lot of substantial orbits, this can easily be misunderstood by quasar red noise. Like red noise is of course a power spectrum which like peaks at like longer periods. So like AGN is a perfect mimicker of binary periodicity, and therefore we need this additional telltale signature to be able to point at the right galaxy if we want to understand if there indeed is a binary or not. And one of the other ways, one of the other observational signatures that have been found so far in just one source, which is also immediately my favorite black hole binary candidate, is called Spiky. It was found in the Kepler data observed in 2010. I put the large Kepler phone number here on the screen as well. But here's the data on the right, which immediately also showed like how incredible Kepler was, with like it's like small error bars, which are much smaller than the previous plot. Like it also has a beautifully time sampled light curve, and you see that you get this like sawtooth like pattern, which is Doppler modulation potentially of an eccentric orbit, and it's sawtooth like because like the radial the velocity along the line of sight is not changing in a sinusoidal behavior anymore because parts of the orbits are faster than other ones. And then exactly here at the center, where you would expect that the two black holes align with each other because you don't have any Doppler modulation there, there's this massive spike. And this is, of course, why this object was called Spiky by you et al. And the idea there is that given that you're looking so close edge-on with respect to the black hole binary, gravitational lensing can enhance the amount of emission that reaches us as observers, because the foreground black hole will act as a compactifier, a magnifier, and more light reaches our telescopes as this occultation happens. But a lot of this modeling is done by not taking full GR into account, by doing some like rough approximations of the amount of amplification. There's no finite source sizes here. There's like all point sources, just a light bulb moving behind a looking glass. So there's some need for sophisticated models to understand like what can we really do with these signals if we actually measure them. That's what I've been doing in my time at Columbia and at the Flatiron Institute. And one of the tools that I use for that is called general relativistic ray tracing. This is an algorithm that uses a virtual camera somewhere outside of your simulation domain. You can launch rays for every pixel on this camera. These rays are used as initial conditions for the geodesic equation, which gives you the equation of motion in curved space-time. And as you compute these trajectories, you also solve the radiation transport equation to get images of black holes. So you can do this for single black holes, as I did in my PhD. Like an example of that here is shown on the right in the context of PhD. You can also expand this and then do this for a black hole binary. So before I show that result, I want to like give a general sense of what a black hole image looks like and what features to look out for in the remainder of my talk. So in general, like you have this lensing here on the top and the bottom. There's an accretion disk just in the equatorial plane, but due to the lensing, you can see behind it. Secondly, there's Doppler boosting. One side is brighter than the other side because of equatorial motion of the gas. Thirdly, there's a photon ring in this specific example, but the visibility of that will depend on at which radius the accretion disk truncates. So I will have some models where the accretion disk is actually further in and you won't see this photon ring, and vice versa, and then you will see it. And of course, there's the black hole or a black hole shadow in the center, which highlights the size and shape of the gravitationally lensed black hole itself. So this is then an actual model where I have two black holes rotating each other, viewing angle of around 87 degrees, a binary separation of like 100 gravitational radii. It's an equal mass system. You can't see the photon ring because the inner radius is all the way towards the event horizon and not all the way to, not only just to the ISCO. So you can't see the photon ring itself. And this is like an image that peaks around the X-ray. And as the two black holes will start moving around each other at occultation, you will see that the background is deformed and warped around it and will potentially then also do this magnifying that we see in the case of spiking. So and then it happens, of course, again, as the other one moves in front of it. So how does this look like if we look at light curves? So this is another example of my 2022 paper. This is a viewing angle of 90 degrees, same binary separation, same equal mass. So this is perfectly edge-on. Here on the top, you see a couple of, oh, I'm actually in the way of my own images. Here on the top, you have like different stages of the orbit lensing event. Here on the bottom is the light curve as a function of orbital phase. So this is like a normalized flux. And here you see that this spike of this magnification event actually has a signature in the center. And this is all because of the finite source size that I implemented instead of the infinitesimally small source sizes that are typically used in these models. Because what happens? Like, imagine you have this foreground black hole, which acts like a looking glass, and the background source is a big ray. So as you're moving from left to right, first you have emission that you can lens, then you hit the black hole shadow where it is dark. The amount of emission goes down because there's nothing to amplify. And on the right side, you hit this ring again, there's stuff to amplify, and it goes back up. So the idea that I had was like, okay, that's actually quite interesting, because if this nicely correlates with the black hole shadow size, this signature could potentially be used if the universe gives us objects in this specific orientation to be able to measure the black hole shadow size, and on top of that, do tests of GR on cosmological skills for black holes way outside of the range of the Event Horizon Telescope's capabilities, for example. So I did a little bit more digging. I did this model where I actually pushed the accretion disk a little bit more outwards and I made it a little bit thinner. And then here you have a zoom in of one of these flaring events. And then I overplot this like region where I expect, okay, the shadow is this portion of the entire orbit. Does it match up the duration of this peaking event? And as you can see here, like it nicely matches up. Like you can definitely get an indication of how large the shadow is in the optically thick case, and for the optically thin case, where you have this photon ring, this very nice sharp feature, it perfectly overlaps with the prediction that this signature would be shadow induced. So that's great. The odds of this, however, like I can almost hear you thinking, although you're like 6,000 miles away, like that's great, Jordy, but like the probability of this is probably looking for a needle into in a haystack. So how to find this? And for that, we all will need big numbers, because the window of the inclination is super small. You need to have a binary that's oriented edge-on in such a way that the black hole binary is within the Einstein radius of the foreground binary. So we're talking about like a few degrees at most. If you look at the current data that we have, like 10 to the 9 solar mass black holes with periodicities of typically a year, then this dip will be like a few days. So if it is only a few degrees at most, then the probability of this, of observing this, we're actually talking about like a few percent in the current data, say 1%. So following up the current candidates, these 10 to the 9 solar mass binary black holes, like 150 sources, 1%. Well, maybe we're lucky. Maybe there's one. Maybe not. Maybe we'll need more. And then there's, of course, LSST, Vera Rubin Observatory, which is coming online very soon. They're going to do an amazing survey of like 100 million AGN targets. So who knows? There is a whole zoo of AGNs out there that we will do a very high time resolution. And we recently did a paper with an undergraduate at Columbia University, Kevin Park. It's currently in prep already on arXiv if you're curious, where we actually use like illustrious data to predict what the mass ratio distribution is. We looked at the quasar luminosity function to get a distribution of masses as a function of redshift, and we predict based on like assumptions on the percentages of like the probability of finding those as a function of mass ratio, distance, etc., that there might be a few dozen of these dipping features in the potential LSST data. And on top of that, and maybe more relevant also for NASA, of course, also like pre-merger electromagnetic emission of LISA sources, where we know that there is a black hole merging there within the LISA error box. Then with like X-ray missions or like other NASA-based missions, you could also look at like pre-merger emissions now. So yeah, that's the most of the things that I worked on so far. So a step into the future is like, what are open questions? Well, the model is very...
Sorry, can you wrap up in 20 seconds? We're already...
Yes, I'm almost done. This is my final remark. Yes. So for the future, like we have analytical models now, and the next step with my whole proposal, I hope to take this a step further, make it all time variable, get magnetic fields involved, get intrinsic time variability with GeoMHD simulations, and hopefully we'll be able to say even more about these beautifully rich systems. That's it.
Okay, we can take one quick question maybe while Keith is coming up and we can change the slides. Anyone? I can ask one in the meantime. So if you don't have an independent measurement of the mass, is that something that you get from the shape of the dip? And are there other properties of the black hole that you can measure?
The mass is actually pretty tightly constrained already by the overall periodicity of the signal. So in the case of spiky, the sawtooth pattern already gives you independent mass measurement, which you can then cross-compare with the size measurement of the black hole that you get off the dip. So that together gives you your GR test.
Okay, great. Let's thank Jordan. Next up, we have Ethan.
Okay, well, first, let me just thank the organizers for, is this not loud enough? Can people in the back hear me? Is this okay? Oh. Is this better? Yeah, I mean. Okay, I can do this together. So yeah, first, let me just thank the organizers for putting together this wonderful symposium. I've had a lot of fun the past 2 days and I'm looking forward to the next couple of days. So for those who don't know me, I'm a new Einstein Fellow that was originally here at Caltech, but I'm now moving to Cornell University. And a little fun fact, actually, the last time I was in this room and actually on this stage was when I was defending my thesis. So hopefully this talk is a little bit more fun. And so today what I'd really like to talk about is Einstein's theory of general relativity and really the ways in which we want to test Einstein's theory in the near future. And this is because while Einstein's theory is remarkably successful, we know it has to fail. In particular, Einstein's theory of general relativity is inconsistent with the physics we use to describe the microscopic realm, namely that of quantum mechanics. So at the end of the day, we need some alternative theory of gravity that unifies these two realms. And while we can try to intuit what this theory should be purely from a mathematical perspective, kind of our leading efforts really haven't been that successful. And so it would really be helpful if we have some data from our universe to kind of guide our theoretical motivations. And so kind of the best way we can hope to do this in the near future is using gravitational wave observations. So here what I'm showing is the first gravitational wave observation that we made in 2015 with the LIGO-Virgo-Cadre collaboration. On the top left panel, this is what we observed in the Hanford detector. On the top right panel, this is what we observed in Livingston. And effectively what this measures is the amount by which the space-time within these detectors is expanded and contracted due to the merger of two massive black holes within our universe. And so you can see from the raw data, there's clearly a signal there. But now the question is that if we've observed this astrophysical phenomena within our detectors, how can we actually compare it to what Einstein's theory predicts, right? If we want to study the data and do a test of our theory, we need to know what that theory predicts. And unfortunately, Einstein's equations are incredibly challenging to solve. And for the case of binary black hole coalescences, there's really no way to solve them with pen and paper. And so instead, what we rely on is a field known as numerical relativity, effectively taking Einstein's equations and putting them on a supercomputer and letting the computer do the work for us. So what exactly does numerical relativity consist of? So for simple cases, let's just imagine we're doing a binary black hole merger in vacuum GR. Now, Einstein's equations themselves don't care about the coordinate system that you use. But when we work with a numerical relativity simulation, we need some coordinate system that we can evolve on our computer. And so kind of the most natural thing to do is simply take Einstein's equations and write them in what we call 3+1 form, namely 3 space-like dimensions and 1 time-like dimension. And so if you take Einstein's equations and you express them in this form, you effectively get 2 sets of equations. Constrained equations, which tell you what your initial data has to be. So they kind of say, if I have 2 black holes of these masses and spins, what does that initial space-time slice look like? And then you have evolution equations, which tell you how that initial data has to evolve in time. And so if you set up your numerical relativity code correctly and you perform this evolution, effectively what you obtain at the end of the day is the space-time metric as a function of your coordinates, namely some radius and some set of angular coordinates. And for practical purposes, right, we can only simulate some finite volume of spacetime because the larger spacetime you simulate, the more expensive it is. And so our final output is really just a metric at some finite radius. But when LIGO observes a gravitational wave event, they don't observe the metric, they observe a gravitational wave. And so the natural question is, after we've computed this metric in our simulation, how do we extract a waveform? Well, there is kind of a natural idea, which is you could just take that data at some finite radius and subtract what you expect the background metric to be. And then you would just kind of have the perturbation about the background, which you could call your gravitation. The issue with this is that the LVK a priori doesn't know how far away their events are. So providing data at some fixed radius really isn't useful for them because they need some model that's generalizable as a function of radius. So this kind of first naive idea doesn't really work. And instead, what we want to do is extract the gravitational wave infinitely far away from this event in a region of spacetime called future null infinity. And so the reason we can do this is because if you take the metric which describes arbitrary asymptotic radiation, so any astrophysical event, the part of the metric which describes the perturbations to the angular part, namely this gravitational wave, exhibits this fall off with respect to 1 over r. And so infinitely far away, the leading term that's going to dominate with respect to the background term is this term here, which is what we call the gravitational wave strain tensor, or just the gravitational wave strain. And so you might worry that, well, if you do this kind of perturbative expansion, are you losing information by throwing away this second order term? And so you can actually do a simple calculation for typical LVK events. And what you find is that the second term is a 20 order of magnitude smaller correction. So it's really not at all important for real detections. Okay, so if you kind of take this idea and you think about extracting a gravitational wave infinitely far away, you obtain a picture like the following. So here what I'm showing is the output of a numerical relativity simulation whose inspire parameters most closely resemble GW15914, this first detection. And so this is really what people think of when they think of a gravitational wave. This is kind of the picture most people have in their mind. But it turns out this is actually entirely incorrect. And this is because the way this waveform was computed has a flaw in its numerical algorithm. And so at the start of my PhD, we kind of implemented a correct algorithm in our numerical relativity code. And the output we got is instead the following. And this is really what gravitational waves look like in nature. And so the difference between these two pictures can effectively be summarized in one physical phenomenon, something known as a gravitational wave memory effect. But what exactly is this phenomenon? Well, if you think about the way in which gravitational waves distort spacetime, we typically think of them in terms of their polarizations. And so if you have a plus polarized gravitational wave and a series of test particles, as that gravitational wave passes through the plane, the spacetime between these particles will be distorted with respect to the peaks and the troughs of the gravitational wave. And what the memory effect says is that after the gravitational wave has passed through, the space-time will remain permanently distorted. And so what this is to say is that any gravitational interaction permanently changes the space-time between two initially co-moving observers. So gravitational waves are changing our universe all around us permanently. Another important feature about this phenomenon is that it's a nonlinear prediction of GR. So if we observe it, we can learn very interesting features about the unique nonlinear nature of general relativity. The issue, and part of why we care about memory effects, is we've actually never seen them. So even though we've seen roughly 100 gravitational wave events, we've never identified a part of the signal that looks like a memory effect. And part of the reason why is memory is extremely low frequency, and our detectors really aren't that sensitive to these frequencies yet. But the hope is that if we observe this effect in the near future, we have a new, intriguing, and unique way to kind of probe Einstein's theory of general relativity. And perhaps the most interesting feature is that these memory effects turn out to be intimately connected to symmetries of this region of spacetime called functional infinity. And part of why this is relevant is because this turns out to be closely related to the notion of holography, which turns out to be relevant for people trying to formulate theories of quantum gravity. And so let me elaborate on that a little bit, because it's a little subtle. But so it kind of all stems from Noether's theorem. So as a reminder, Noether's theorem says that for every symmetry of a system, there's a corresponding conservation law between some kind of charge and some kind of flux. And so if we want to study Noether's theorem in a gravitational context, we really want to study the symmetries of the region where these gravitational waves live, which is this region that I highlight in blue called functional infinity. And so you might think, well, if I just have empty space, the symmetries of empty space are the Poincare group. Namely, 10 transformations, you have 4 space-time translations, 3 rotations, and 3 boosts. And so you might naively think that if I go infinitely far away to functional infinity, I should probably still have these same 10 symmetries. But it turns out that's not the case. And so one way to see this is kind of through the following thought experiment. So imagine you have a collection of observers surrounding some kind of event, say a binary black hole merger. If these observers know their relative positions, they could communicate with one another to synchronize their clocks such that they receive the same information at the same time. But as I push these observers farther away, it takes them longer and longer to communicate with one another. And as I push them infinitely far away, they actually become causally disconnected. So for each individual observer, each point on this celestial two-sphere, I actually have a freedom to translate each point of the two-sphere independently. And so it turns out that at functional infinity, you actually have an infinite set of symmetries, which correspond to direction-dependent translations. And so this should seem eerily familiar, namely, if you look at these transformations kind of highlighted in this diagram here, these kind of correspond to permanently moving certain points on your sphere. And if you think about permanent changes to your space-time, this sounds eerily familiar to memory effects. And it turns out that these symmetries are actually exactly connected to memory effects. In particular, if you take these symmetries and you perform Noether's theorem, or really a modified version of Noether's theorem, since we're dealing with general relativity, you obtain a balance law which says that not only do you have a balance between a charge and a flux, but you also have a balance with the strain. And it turns out that memory effects are actually exactly captured in these charge and flux terms, and yield that if you have a net change in your charge or a net change in your flux due to some kind of energy, you have a net change in the strain. And where this becomes interesting, especially with regards to the high energy theory community and people studying quantum gravity, is in 2013, it was actually realized that not only do you have this connection between memory effects and asymptotic symmetries, but there's a third component that forms this, what's called an infrared triangle, that says memory effects and asymptotic symmetries are related to these things called soft theorems. And unfortunately, I don't have time to go into what soft theorems are, but you can effectively just think of them as corresponding to quantum gravity. They effectively describe how to study the S matrix, the scattering matrix, in a quantum theory of gravity. And so a lot of people are excited by memory effects because they give us a realistic way to observe something that might exhibit signatures of quantum gravity. And so what we need now is, because we only recently got this new code framework to calculate numerical relativity waveforms that exhibit memory, we need new models that exhibit this effect. And so currently we have one model for binary black hole mergers that exhibit memory effects, but it only spans 3 dimensions of a 9-dimensional parameter space. And so in the near future, I'm going to improve these models to span more of our parameter space to hopefully help us detect memory and really push Einstein's theory to the limits. So with that, I'll just thank you for your attention and ask if you have any questions.
Questions? Yeah, good.
So this might be kind of a naive question. But so this memory is really interesting. If you could measure this for a bunch of different events, right? Are there predictions about, you know, some kind of isotropy of like if you average those things together, should it go to 0 or not?
Yeah.
Right? And what does that tell you?
I love this question. It's a great question.
Repeat the question.
Yeah, so the question is, if you consider this effect kind of accumulated over a number of events, does it average out, right?
Yeah.
So there's this unique phenomena in 3 dimensions where if you perform a random walk, you actually never return to the origin. And so what this means for memory effects is that because you can think of the memory effect from some random binary as a random walk in the distortion of space-time, it will actually permanently drift away from 0. So if you think of it as a stochastic background, there should be a non-trivial background in the distortion of our universe due to memory effects. There's been 2 papers on this. They both underestimate the size of this effect. It would be interesting to do it properly because I think it could actually be pretty significant, but that's to be determined.
That's cool. Thanks.
I think Ward.
I was curious if you had any time to give a short summary of what a soft theorem is.
Yeah, so effectively what a soft theorem is if I do a gravitational scattering, so if I scatter 2 particles in a gravitational context, you get some kind of output particles, right? And there's many different output states you can get. Namely, you can just have the 2 particles come out, and that's one possible outcome. But there's also an infinite number of contributions to these types of diagrams where you radiate 0 energy gravitons, which is why they're called soft. Soft just means 0 energy. And so it's effectively just a soft theorem tells you the way in which these types of diagrams contribute to your overall scattering amplitude. There's just kind of a special little factor you have to account for these 0 energy gravitons that escape to infinity. It's related to Weinberg's soft photon theorem in electromagnetism, but it's just a gravitation version.
Okay, maybe one final question while Leah comes up and we can do the transition. Yeah, I think David.
Specific question. Different.
Yeah.
In the work class simulations where we use the matter effects in gravitational waves, we see what memory effects, we see what matter and gravitational asymmetries. And at many times there's permanent offset in the metric because of a large electron projectile. And this should be detectable with next intersect
Yes.
like SO and ET for a full range of stellar masses.
Yes, absolutely. So yeah, when I talked about memory effects, there was this strain equals charge plus flux. So in binary black holes where you don't have matter, the memory is entirely sourced by this flux of energy. It's a direction-dependent energy radiation. Yeah, so what you're talking about, David, is this change in the mass. So if you have a change in your quadrupole moment, a permanent net change, which we see in supernova or neutron star mergers, then you get a memory effect due to this change in the mass, and it actually dominates over this flux contribution. So I completely agree. Yeah, with in future generation detectors, not only will we see memory in single events from binary black holes, but we'll definitely see it from supernova. Yeah.
Okay, great. Let's thank you again. Next up, we have Leah Medeiros.
Okay, cool. Hi, everyone. I'm Leah Medeiros, and I am a Einstein Fellow at Princeton University. This is my second symposium of these. This is supposed to be spinning. Sorry about that. I should also say that in a few months, I'm actually going to be moving to the University of Wisconsin-Milwaukee for a faculty position. So if you have some awesome undergrads that are really interested in black holes or the Event Horizon Telescope or machine learning, send them my way. So my proposal is based on this algorithm called PRIMO. It's a machine learning based algorithm to analyze EHT data and reconstruct higher resolution images based on simulations like the one that you see here. So of course, the first step in any algorithm like this is to create your training set. And so I did run a really large data set of simulations. We're going to do a little fly through for you right now. But one of the things that I think is really cool about the symposium is that last year I came to the symposium and I met another fellow, Matthew Liska, and we started chatting, and he runs simulations like these as well. And we actually wrote a collaborative AAG that just got funded. And so this training set is going to get a lot more exciting and a lot broader very soon because of this symposium, which I think is really cool. What I want to highlight here, by the way, is that a lot of these things look like little donuts, but a lot of these things do not look like donuts. That is on purpose. The algorithm doesn't actually care at all about the actual physics, but what it does care about is image morphology. So we go out of our way to include as many different image morphologies as we can in the training set to make sure that we are not biasing the results. So how does the algorithm actually work? So PRIMO stands for Principal Component Interferometric Modeling. I am not great at naming things. It is a bit of a tortured acronym, and I'm so sorry. If you have ideas, suggestions, any of that, please do let me know. But anyway, it's called PRIMO. Each of the images in our training set acts like a vector in this hyperdimensional space of vectors, and we use principal component analysis to find a basis for our vector space such that we can perform really effective dimensionality reduction. Here I'm just showing you the first 3 PCA components because I can only draw in 3 dimensions, but of course we do actually have more than just 3 PCA components. And so what we can do is we can approximate an example snapshot from the simulation like you see here with a linear combination of these PCA components. Now, with only 3 PCA components, you really don't do that great of a job, but you do get the main features in your image. However, if you were to use, let's say, 20 principal components, you do a much better job. Okay, so what is this algorithm actually doing in practice? Why is it that we can do this? What are we really learning? So what you're looking at right now is Fourier domain. The black dots are the locations in 2D Fourier space where the EHT observed the black hole in the center of M87 in the 2017 observations. Those are the observations that were used for the very first image of the black hole that we published April 10th of 2019. What you will notice, I'm going to try to use the pointer, so bear with me. What you will notice is there's a lot of empty white space there. Yes, we don't like that. That's bad. That means that we have no idea what's going on in that location. And so mathematically, you can actually prove that there's an infinite number of images that is consistent with our data because you can put whatever number you want in those white spaces anywhere, 0 to infinity. So any of those options will give you a different image. So no matter what you do need to make a decision about how you're going to fill in the gaps. And the way that we do that with PRIMO is that PRIMO actually learns the correlations between nearby regions in Fourier space and uses that to fill in the gaps. So you can calculate analytically the correlation length, and that's what it looks like visually, such that everything that you see in green is correlated with at least one data point from the data, and that is how we actually fill in the gaps with PRIMO. Okay, I'm going to go through this fairly quickly because it's just a recap from last year. But if you use one of the other imaging algorithms, and if you try to observe a uniform ring, you will tend to create images like this that have these little bright spots along the ring. You'll notice that that also does exist in the real black hole images that we've published, but we do not get that kind of feature with PRIMO. So this is the original GRMHD snapshot. We did a synthetic observation and a reconstruction of PRIMO, and we do not create those bright spots along the ring like we do with these other algorithms. And so just to kind of summarize, we don't create these not artifacts. We have the ability to reconstruct pretty complex source structures, and we're not limited to like specific realizations of the turbulence, but we can kind of fit any image that lives in this like broad image space that we've created. And just to kind of, emphasize that point, the image that you see here has a black hole spin of 0.7, and here I've actually trained the algorithm only on black holes of 0.9 spin. And so we're able to reconstruct an image where the data set for that particular training set is completely disjoined from the image itself, which is pretty cool. Okay, so that's where we were last year. This is the original M87 image. I came to the symposium and I showed you this. This is the PRIMO image of M87. It's completely consistent with the EHT. The ring width is smaller by about a factor of 2. This is a little bit hyper-resolved. This is what it looks like when you make sure that you're not hyper-resolving the image. This is actually at the real resolution of the array. It's a significant improvement from what we can do with other algorithms. Okay, so what have I done since then? It's been a year. What have I been up to, right? Well, I actually rewrote pretty much the entire code, which is not super glamorous and does not give me fun things. But the motivation for why I rewrote this whole code is the instruments itself. So this is what we had in 2017. And this is what we have right now. We've added the Greenland telescope, NOEMA, and the Kitt Peak telescope as well. We filled in for a space a little bit. But what I'm really excited about is that we're actually observing at 0.8 millimeters now. So we had been observing at 1.3 millimeters, but now we're actually observing at both wavelengths. And the pink that you see here is the baseline coverage that we hope to get at 345 gigahertz, which is at 0.8 millimeters. I should emphasize that this is not accurate for what we are at right now. This is a little hopeful for the future, a little optimistic, but this is where we're going. And so I should emphasize that just a few weeks ago, the collaboration did publish the first fringe detections at 345 gigahertz, which is crazy exciting and amazing because this is the highest frequency DLBI that humanity's ever done, which is really cool. Okay, so given that we are trying to do these simultaneous multi-wavelength observations, I should also say, soon there will be a third wavelength as well. Hopefully, we're still proposing for this. Hopefully the proposal gods will be kind to us, but we're trying to add 90 gigahertz as well. Okay, so with all of that in mind, I wrote a new version of Primo, which is multi-wavelength Primo. I'm clearly very good at naming things. But the idea here is that we can reconstruct, in one single Primo fit, we can reconstruct an image that has both wavelengths, but we are still reconstructing a different image at each wavelength, but in a way that you actually take into account the correlations between the wavelengths. Let me actually try to explain that a little bit better because that was not great. So far, what people have been doing with these multi-wavelength observations is assuming that the image looks the same at 345 and 230, and then doing a single image fit for that. Okay, and what you can see, this is 230 here, the blue, 345, the green, and what you can see is that they are pretty similar, but they are actually different. The first image here on the left is a two-color image. The fact that it's not all exactly the same color shows you that there is actual difference between the two wavelengths, okay? Otherwise, this would all be perfectly the same color teal. And so anyway, so we can learn the correlation between the wavelengths and perform a single fit simultaneously that will give you this multicolor image, learning those correlations. And so what's really cool about the new version of Primo is that not only can we do this for one epoch, but we can actually make a movie, which is pretty cool. I should say that this is a very ambitious movie. This is not realistic at all. This is, a simulation. But just last night, I did run for the first time a synthetic movie for you guys. And so the top row here, this is just the original images from the simulations blurred a little bit. And on the bottom row, this is what happens when you do a synthetic observation with Primo and actually do the fit. And I can emphasize that if this is the M87 black hole, the movie I'm going to show you is what you would see if you were to observe every single week for 16 weeks. And the whole movie that I'm showing you is 8 seconds, but it's going to loop to make you think it's longer. So I'm cheating slightly. Whether or not this is a movie versus a time series of images is a whole other thing. I actually think that 16 weeks straight is going to be really, really hard. Okay, anybody who's ever tried to get time on Alma can attest that this is like a really, really hard ask. So hopefully someday, but you gotta shoot for the moon and put this kind of stuff on your proposals and hope for the best, I guess. Okay, so with that, I will leave you with my summary. So the multi-wavelength Primo can do multi-epochs with a single M over D posterior. I didn't really touch upon this, but the idea is that if you observe in 2017, you observe in 2018, you can actually combine them and get a single posterior on your mass over distance measurement, which is really cool. You can also do the multi-wavelength, like I just showed you, in a way that you're actually learning the correlations between the two wavelengths, but still creating two different images. We can also do multi-band, which I'm not going to get into, and you can make a time series of images. Okay, with that, I'll take questions. Thank you.
Yeah, 4.
I had 2 questions. One, did I capture that you're actually getting band 9 observations that you're proposing for? Or like what band?
So I'm a theorist. It's 230 and 345. is what we're operating at right now. We are hoping for 90. Most of the EHT observations, like most of our telescopes would not necessarily do 90. By the way, it's actually 86, but I'm estimating it as 90. But effectively, what we're trying to propose for is a significant overhaul of the instrumentation with like MSRI. That would make every telescope observe at least 2 wavelengths simultaneously, maybe 3. I don't know the bands because I'm a theorist, so I'm so sorry.
I asked because band 9 is extremely rare because there are only a handful of nights per year that you get the kind of resolution that allows you to have it. So I was wondering if that's what you were proposing for with the new band.
Band 9 is 650.
Okay. People have run simulations at 650. The LBI at 650 is really hard. Hopefully we'll someday get there, but I think that's gonna be really hard. 345 is definitely harder than 230, but it's not. Thank you. I don't know what the bands are, but I do know what 650 is. So you had 2 questions.
Yeah, the second part was more about the Primo work. I was wondering what ways you're able to test for like hallucinations or outputs that you might not necessarily expect, what fractions of time those might occur, assumed by like splitting up training and testing data.
Yeah, so a couple things for that. In a longer talk, one of the things I talk about is the original EHT analysis of M87. And I really emphasize that we tried really, really hard to kind of cross all of our T's and dot all of our I's and really prove that this thing has to be an image. And if you want, I can show you later, like the specific details in the actual structures of the data that really convinced us that this has to be a ring. And so the way that I'm operating with Primo is now that I've proven that it's a ring, I personally feel comfortable making that assumption moving forward. So it is a ring-like feature that I am comfortable with. Moving past that, I think that there's a lot of strength and kind of power in the fact that we do have all of these different independent algorithms as well, right? So the fact that like Primo is consistent with all these other algorithms also gives us a lot more kind of confidence, I guess. And then the other thing I was going to say is that what I'm working on right now that this new version is done, with the new version, I'm going to do a really comprehensive calibration of it, where I'm going to apply this to like thousands of images and really look at kind of how well can we reconstruct all of the salient image features and what are the error bounds on those.
Any other questions? Yeah.
Really cool work, and someone who shares a lot of visibilities on it, really interested in something like Primo. So I guess like part A of my question is this something that we can analyze to like any like interferometric observation, or is it uniquely suited to what you're doing with these VLBI electrical optimizations? And then my second question is maybe a little more granular, and it's that are you actually learning like an optimal weighting scheme given the like sky brightness distribution that you expect for these when you're like putting them into like the clean like algorithm? Or
What do you mean by weighting scheme?
well, so you're talking about these like visibilities that you're kind of fiddling around by having some correlated signal there.
Yeah, okay.
And so I mean like when as an observer, like I think like, okay, so what you're doing is you're going in all of visibility to be weighted when you're transforming them to
Okay, great.
and so I'm just trying to connect it to.
Yeah, okay, so I'm gonna answer the second question first. Okay, so this is completely independent from something like clean, and Primo itself does the inverse Fourier transform.
Okay.
And so I proved that the PCA and Fourier transform, they're both linear, they commute, right? And so I take the PCA in image domain, then I take the Fourier transform of those, and literally the way the algorithm works, it's an MCMC that fits a linear combination of those, of the Fourier transform of the principal components directly to the data in Fourier space, allowing for a few additional parameters such as all of the principal components can be rotated together, and they can all be scaled together, and that's what gives you the posterior on the orientation of the spin axis and the posterior on the mass over distance.
Okay.
Your other question is really well timed. I am working with Cassandra Hall at Georgia State with a student for applying this to exoplanet simulations with ALMA. So yes, but each application will require a very careful analysis of kind of really, you just want to optimize it, right? So for example, like there are certain things that you really do want to include in your PCA, and there's other things like what I just said, this rotation or this scaling, that are much more efficient if you include them as separate parameters. And so that's the kind of work that we're doing with the student right now is really optimizing how this can be implemented for something like exoplanets in the best optimized way.
So it's really trying to really forward model the observations, given some very reasonable guess for what the source properties are, right?
Yeah.
Which might tailor like the different cases.
Yeah,
Okay.
exactly.
Thank you.
Yeah.
Okay, let's thank Leo again. All right, and the last speaker of this session is Alex Dickon.
Right, well, hello everyone. I'm Alex, a newly minted Einstein Fellow at the Institute for Advanced Study, and I will try not to keep us too long from the break. Now, because this is a Hubble Fellowship Symposium, I have to start here with this just classic image, because in addition to all of these beautiful stars, this gas and this dust, when galaxies merge, they bring with them in their centers supermassive black holes that can go on to form binaries. And at the early stages of this binary evolution, right, the binary is dominated by things like dynamical friction with the dark matter halos those galaxies brought with them, or stellar scatterings as stars wander close to these binaries, receive some gravitational kick, and carry off energy and angular momentum. But as the binary shrinks, those processes become less and less efficient at helping the binary shrink further. And eventually the binary's evolution is dominated by things like gravitational wave emission and interaction with gas that is thought to abound in the centers of these galaxies following mergers. And that's that latest stage with the binary interacting with gas is what I'll be focusing on from sort of a parsec down. And the presence of gas is particularly interesting and exciting because it might give us some way to identify these binaries at scales that are too small to resolve in images. And looking forward towards missions like LISA, we might be able to identify some sort of electromagnetic counterpart to these gravitational wave events. But in thinking about binary accretion, the first question we have to answer is whether binaries can actually accrete. And although you already kind of spoiled this, many people for decades have thought, just realized that the gravitational torques from these binaries on the gas will be very, very strong, much stronger than the typical stresses you might expect transporting angular momentum through the disk. And people have worried that these black hole mergers might actually be dark if gas is prevented from accreting onto the binary. But thankfully, we've been able to run simulations, and in most cases, yes, binaries can accrete. So from very early smooth particle hydrodynamic simulations of viscous disks to modern general relativistic magnetohydrodynamic simulations, we can see that although the disk is quite disturbed, the binary still manages to accrete. And that proceeds something along these lines. So we can see here that the disk has been strongly affected by this binary, as it's opened up this large eccentric cavity in the disk. However, every time one of these binaries approaches the pericenter of this eccentric disk, it strips off some material from the cavity's edge. Now, some of that material is captured by the binary, bringing with it lots of energy and angular momentum, but other material receives this strong gravitational impulse from the binary and is flung away through the cavity, carrying off energy and angular momentum. And it turns out that in these near equal mass ratio systems, it's actually just this balance between captured versus material flung away that really governs the orbital evolution of these systems, with relatively negligible contributions from things like resonances or accretion. Additionally, from watching these systems, we can actually get a sense for some of the different periodicities we might expect to observe in these systems. So every time one of these black holes approaches the pericenter, it accretes some material, and that accretion rate onto the binary is modulated on the binary's orbital period. Or for an equal mass binary like this one, half that thanks to symmetries. Additionally, we can see that the surface density around the edge of this cavity is not uniform. And every time this higher density material approaches the binary, that will temporarily increase the accretion rate, giving it some periodicity on the orbital period of the cavity, which for this system is roughly 5 orbital periods. Now, looking at the orbital evolution, this is just for a large collection of disks at different thicknesses. So thick disks are up here, thin disks are down here, just surveying a bunch of different disk viscosities. So low viscosities are over here, high viscosities are over here, very efficient transport through the disk. And we see that for thick disks, right, so this is plotting the rate of change of angular momentum, or sorry, the rate of change of the binary semi-major axis normalized by the binary accretion rate. So thick disks basically uniformly lead to out-spiraling binaries, actually. So gas being present around these binaries will cause them to out-spiral, delaying these black hole mergers and moving them to larger separations. On the other hand, if we have thinner and thinner disks, like we'd expect for sort of classic models of AGN disks, the binary can inspiral fairly quickly. So in roughly one mass doubling timescale, some of these systems might shrink their semi-major axis by a factor of 2 to the 16 or so. Now, all of this that I've showed you so far has been focused on equal mass binaries. We can look at unequal mass systems as well. Some things change, some stay the same. This is covering roughly the range we expect for different mass ratios that form as a result of galaxy mergers, from very minor mergers over here to major mergers on the other side. And although when we go to unequal mass binaries, some of the symmetries are broken, the binaries still open up this deep cavity in the disk. The accretion flow is still very variable. And as we move to more and more unequal mass systems, right, the gravitational potential gets closer and closer to that of point mass. The cavity gets smaller and a bit less eccentric, but we can still see this is far from the sort of quasi-steady state we might expect in sort of a planetary mass ratio system. Additionally, as we have broken the symmetry between the two black holes, right, we now have a more massive primary, a less massive secondary. We can see that the typical gas density around the orbit of the secondary is much higher than that of the primary. So in many of these systems, especially those with very thin disks, the secondary tends to accrete at a much higher rate. Although we can still see some of this material accreting directly onto the primary through L3, as well as moving into the disk around the primary through the disk around the secondary. We can see that in a little more detail here. So this is showing just a time average of the surface density in one of these binaries, along with streamlines showing the flow. And things like the accretion rate onto the secondary versus the primary, this will govern how the mass ratios of these systems evolve as they contribute to the gravitational wave background, for example. This exchange of material from one accretion disk to the other ends up depending very sensitively on things like the effective viscosity, just whether you have an alpha viscosity with a r to the minus 1/2 power law or something else. This can greatly affect the amount of accretion onto the less massive black hole by factors of 2 or 3 at some mass ratios. Additionally, this sort of thing depends a lot on the disk thermodynamics. So if you go to hotter disks, it's much easier for matter to pass from one disk to the other. And if you go to a very, very thick quasi-spherical flow, of course, most of that material will just fall ballistically towards the center of mass and get captured by the primary. Now, everything I've discussed so far has been in sort of the widely separated limit where the binary evolves on a relatively long timescale compared to sort of the dynamical timescale of the system. In the following, I'm going to focus on the much later stages of the merger, sort of approaching the regime where gravitational waves can really be dynamically important. So here, I'm showing some binaries starting at about 100 RG, going right down until merger. So in both of these, right, so we can see the binary shrinking over time, so it's very, very small. We can't really resolve it in this image. And the disk tries to keep up with it. So at early times, right, so the top row is a very high viscosity simulation where the disk is able to respond very quickly to changes in the binary's orbit. And in this case, the system retains this sort of self-similar structure, moving just to smaller and smaller scales. So these periodicities I discussed earlier just move to higher and higher frequencies as the binary shrinks due to the emission of gravitational waves. Now, in the bottom row, this lower viscosity case, this sort of self-similar structure is preserved for a while, but eventually the binary just starts inspiraling much faster than the disk can keep up. And we can see in the bottom two panels there that the disk is completely different from what it looked like at larger separations. So this very eccentric structure is essentially frozen in, and the binary has left the disk behind completely. It turns out we can also just measure this and predict when it happens fairly well. So over here, I'm just going to give up on this. But this plot on the left here is showing just a measurement of the cavity semi-major axis versus the binary. At early times, these are linearly proportional to each other as we have this sort of self-similar structure. And at late times, as the binary zips away due to gravitational wave emission, they become independent of each other. We can measure the break in those power laws, and it turns out we can predict it very accurately just by comparing the rate of change of the binary semi-major axis due to gravitational wave emission to the viscous spreading rate of the inner edge of the accretion disk. And like most things in astronomy, you can also get sort of an order of magnitude accurate error by thinking about the timescales. Now, connecting this to things that are a little more observable, these are some accretion rate time series for the high viscosity and low viscosity cases that I showed earlier. So each of these windows is zooming in on the region indicated there. For a fiducial sort of 10 to the 6 solar mass binary, these windows are about 10 days long. Although for the high viscosity case, the variability is just so high frequency that that one has a bit shorter of a duration. So in a high viscosity case, as the self-similar structures moves to smaller and smaller scales, that's higher and higher frequencies, as the binary inspirals due to gravitational wave emission, all of this periodicity will just move to shorter and shorter time scales. And in these cases, this larger amplitude variability is actually due to the orbit of the cavity around the binary. And then the higher frequency variability on top of that is actually due to the orbital period of the binary itself. Now, if we go to the lower viscosity case, some of the same patterns appear as well, although in this case, the disk isn't able to spread quite as quickly. So the variability doesn't move to as high frequencies, right? Because the orbital period of the cavity remains longer. And then probably most strikingly, as we really approach merger, going to the very end, the last week or so, the accretion rate onto the binary can drop by an order of magnitude or so. And I mean, as you already discussed earlier, it is within the realm of possibility to really do a nearly full physics simulation of the late stages. And this is one case where the type of system you want to simulate will have very different initial conditions late in the merger, whether you have a very sort of thick disk with very efficient momentum transport or something very thin. And with that, I'd be happy to take questions. Thank you.
Questions? Yeah.
So is it aerodynamic simulation or MHD simulation?
So these simulations, right, so the question was sort of what physics these simulations included. So most of the simulations I showed here were viscous hydrodynamics. This last section included a bit using post-Newtonian orbital evolution as well.
So do you expect like magnetic field can change the accretion rate for secondary?
So I think magnetic fields will be particularly interesting for trying to understand this sort of thing, where we have different, basically, eddy viscosity models for how we expect transport in these disks to behave. And it turns out things like how much matter gets onto the secondary is very sensitive to which particular model we choose. So I think MHD will probably change this quite a bit, along with things like the disk temperature and whatnot.
So can you give this spiral also for the final portions of the merger, depending on the properties of the disk, or is that only applicable at very wide separations?
Yeah, so the question was whether we could get out spirals in the later stages of the merger as well, or just earlier stages. So by the time the binary reaches these separations, the just torques from gravitational wave emission will completely overwhelm anything gas can do under reasonable assumptions about gas densities and whatnot. On the other hand, if you go to maybe a factor of 3 or 4 wider separations, there gas still may be able to play a significant role. Now, this is also for equal mass binaries, for more extreme mass ratios as well. These outward torques may actually delay the merger quite a bit more because the gravitational wave emission will be much, much weaker at more extreme mass ratios. So maybe for MREs, this could be a little more significant.
Okay, let's thank all of our speakers again. We'll be back in 15 minutes at 2:45. Actually, I want to ask you a question.
So is this all like math scale and doing that like the same? Okay, so like if you have solid math,
That was actually my cover slide.
Nice.
Can I test my
Great.
slides really quick?
Yes, it's there.
Thank you. McKinney?
Yeah, but I sent an updated one, like this morning.
Okay. These did come in from this morning.
Okay.
It's 57. So
Okay,
this-
cool.
This should be today.
I did one last night and then this morning.
Okay, this should be today's, but we can,
Either way is
you can pull it up. and see.
fine.
Well, I mean,
It's just
we want
that,
the right one, so.
yeah, the one is slightly shorter to avoid. Okay, cool. This is the right slide because I have to switch out of this slide with this button because it has a cool running video that can lock out. It's fine. I just walk over the computer.
I don't have one.
Yes, okay, this is-
But it does. Okay.
And it works.
Okay, okay. You want to take a look?
Yes.
Oh, you have something good here?
Oh, gosh, geez.
You tell me.
What, it was confusing, I didn't have movies in here, like.
All HGN discs selling that platform just have to be like.
We tried to make it, yeah, we tried to make it like less, dependent on like different transitions.
Alright, great.
Yay. Thanks.
Yeah.
So when. So you actually. So. But they are. And then if the right three binaries get checked, midline build. As well. So actually, there are a few ways. That are actually but it's yeah. Also because. That's what they're saying. When you have. And actually, so you get a lot of large scales, it just seems falls in the list. And they're. So they're sometimes it doesn't have to change the other direction. But keeping this more stable.
Right, I was not blessed.
Yeah, totally, I mean, you can ask.
So what I was just going was. What factors can get when you're in a quite high phase. Like doesn't depend the concentration.
The accretion doesn't,
The accretion rarely actually uses. So if. Okay, so slightly dependent on what the scale and the innermost stable orbit is. But if the black hole is technically a mass, then the accretion for basically supernovas or inflation and gas will accrete with about the same specific angle to the black hole itself. So accretion to them. Although if you have, say, the accretion rate changing the density scale of the disk that would affect the torque's rotation.
yeah.
Right, but when you were saying like thicker disks can give you another spider.
Yes, yeah, so that has to do more with matter being captured by the binary versus forming captured. It changes a little bit the excitation rates of the disk, but that's sort of a minor factor compared to just material just receiving a kick from the binary versus material being captured by it. Okay, but basically the positive torques usually aren't that strong. Okay, but sometimes like what equal masses. Yeah, so you get the magnitudes are very different. So normalized by the accretion rate, which is what people do in this field. The sort of the d log a, d log n is at most maybe plus 0.7 or plus 2 or something. So that's really like centimeter axis versus mass power law is like 2. Okay. Negative, it could be -16 or something. Okay. But yeah, so they're very challenging. If the binary gets too close, then gravitational force will just take over. But there's certainly so for those the binaries I showed, by the time the binary gets that close, the gas is a little bit further away. It can maybe just lead to a small phase shift over time. That's only detectable because those would happen.
Wanted to be here early.
Yeah,
and just
definitely.
finish off.
Bonus points. I think we can probably set up. I think we can give you the clicker. So yeah, go ahead and join, open it up and join the Zoom and see what we can get. I think we can get you hooked in.
The reason I'm stop sharing so that you can start sharing. Yearly time scales, it was increasing, and then it kind of stopped.
And then not connect to audio and just leave it at that.
So when we saw that it was just still increasing at one point. But why would
The presentation.
Yeah, you have something that's causing.
Yes, that's why I was saying.
Yeah, that's what you might think. Also, those models are actually more expensive.
Yeah, I guess.
Yeah, I think the standard QPO model is for extreme mass ratio is probably very
So good. Plug this into yours and you can see if the clicker works.
Okay, yeah, I think
You're right, yeah, no problem.
Sorry. Okay, yeah, that's.
So like the one I use system is also.
Yeah.
Something is also. Increase was getting lower.
Okay, it's fine, yeah.
Because it's.
Yeah.
Yeah. Okay, clicker works.
Hey, hey. Great, so then do I just pull it out and backwards, forward and
Yep, forwards, backwards.
Yeah.
See the laser filter.
Yeah, you can get these ones.
amazing.
Sweet. Okay, good.
Thank
That's
you so
excellent. No, we can get it.
I'll just leave it like this, I think.
It's going, it's ready.
Yeah, I think my battery situation's okay, so I'm just gonna leave it like this.
That's my decision as well, but disk condition is what single binaries.
Singular migration, the longer migration. It really depends on the rotation around the planet.
As you go to extreme mass ratios.
Hello. I just want to make sure that my slides.
Should be correct. What do we have?
Yeah, I'm sorry, I forgot my time. Rafael Skalidis, can you? Okay.
Is this the right one?
Yes, it looks like.
Okay, yeah.
Okay, great.
Then
Thanks a
it'll
lot.
just flicker.
Thanks a lot.
Yeah, of course.
I want to reach out to Are you doing a pretty like
So it's just yeah, they started doing not and I you know
yeah, that would be really interesting.
yeah,
And you know, it likes maybe I'm just about to have, you know, it's there's the mass and the masses it shouldn't maybe you can raise this to and that's why very strongly then or you just very early weeks. Oh, like few days. Yeah, two up to it and how it's take the shot and take the stuff only yeah. So we get to know what is fine. Yeah, and you're sure and they probably that
oh yeah, so yes,
well, I think the interactions, there's so much more than we have in like once. If you're just thinking about that CSS, yeah, just thinking more about like what observables actually use. It's just
yeah,
and so
yeah, composition
of the system, yes.
no, okay, so it's very. I need the first
Yeah, but that's just a composition of the supercomputer, and so.
Yeah.
Well, I don't think we've ever seen that, so just, well, okay, we'll see what the spectrum is.
Yeah.
That'll be the same, yeah. But this is where you might actually be like a really good NLG, yeah, it's like really goes on. There's some smoke gas images.
Yeah, and that's I was explaining us these things I was yeah, really, yeah, yeah. Yes.
Can you just pull this out? Pull it out, that's okay. Okay.
Yeah. I'm not 100% sure with the battery. It doesn't last a full day. So
Okay, that's okay. I think, yes.
and it works, right?
We're going to start. So, hello everyone, welcome back to the last session of this afternoon. And this session is about our local galaxy. Its topics involves like dust observation, magnetic field, and cosmic ray. And our first speaker is Tavisha, and she will talk about multi-scale 3D dust observation.
Yeah, thank you, everyone. I'm Tavisha Damardana. I'm a Hubble Fellow at NYU and a guest researcher at Flatiron Institute. My title is not strictly true for my talk because I've been working on something that I've been very excited about over the last month or so. So that's mostly what I'm going to be focused on. So to get started, I always get this question from a lot of people about why do we care about dust? It's less than 1% of the total baryonic matter. But we have dust basically forming in evolved stars, and it's ejected by stellar winds and nebulae. It's processed in the ISM. It's incorporated back into star and planet formation. So dust really is involved in this full life cycle of matter in the universe. So you might want to get rid of it. You might want to take it into account, but it is important that you do have to be aware of it. So one of the cool things with dust is its ability to extinct starlight. And with that, what we're able to do is finally map the structure of the Milky Way and its ISM. So, and what happened with Gaia is Gaia really revolutionized the field of mapping dust. So we started a while back with Schlegel, Fink, Banner, and David, which basically led to a really nice 2D dust map, but Gaia gave us these position parallaxes and proper motions, which now finally let us map the galaxy in 3D. So I've been working a lot, starting with my postdoc at NPIA and then at Flatiron Institute, and now as a Hubble Fellow on building my astrocartography code distribution. It basically came about with dust distribution, and my dyslexic brain kept saying distribution, so now the name stuck. That's what it's going to be forever. Distribution is fully an open source astrocartography code. It's not limited to just extinction and distances. You can apply it to any sort of absorption parameters. So if you have any absorption feature, you have a distance to your source, you can use it to make a 3D map out of it. And I've been working very recently actually incorporating line absorption, so going into the gas mapping as well. So simultaneously doing dust and gas mapping, incorporating line absorption, things like velocity for the line strength, as well as stellar proper motions to finally start building this 6D view of the galaxy. The 3D part of the code is fully public. And if you're interested in the 6D part of it, please come and talk to me afterwards. And at the moment, given what we, with the capability of distribution, I've mapped the Milky Way out to about 3 kiloparsecs, ranging from 0.1 to 0.7 parsecs in resolution, using a single H100 GPU in about a week. And distribution is built on Gaussian processes. Again, if you're interested in Gaussian processes, please come talk to me. I think it's phenomenal, everything that it can do. I can talk about it for a very long time. So it's built on latent variable nearest neighbor Gaussian processes. I'm going to throw this name out there and not talk about it afterwards. Come and ask me about it later. And we use custom multi-scale kernels to be able to capture the multi-scale structure of the ISM, and then deep kernel learning to be able to expand into the 6D scales.
What is the kernel used for? Sorry.
What
is the kernel used for here?
It's a Gaussian process. So the Gaussian process is built on the kernels.
Okay, so you're using that technology.
Yeah.
Okay.
So this is my map of the Milky Way. Oh, yeah. This is the top-down view of the Milky Way. So you're up and looking down. And this is integrated at -500 to 500 parsecs in Z. So you have this total view. So for context, we are... oh, gosh. I can do that. Okay, so we are over here. And these are some of our really well-known molecular cloud structures. So we've got things like Cygnus over here. We've got Perseus and Taurus and Orion over here. And what's been fascinating me recently with with the structure of the galaxy and this 3D view is what are all these gaps? We've got all these really big gaps that we have things called the giant oval cavity and the Gulf of Camelopardalis. And this this structure that we saw newly with this map, which is the Interraman spur, which we call the Interraman spur under density, but we're not very sure what caused these structures. So this is something that I've been trying to figure out recently as well. And on the right-hand side, we have a zoom in of the inner 1,000 parsecs. Again, we have really well-known molecular clouds, but there's these massive gaps that we have in the structure of the Milky Way. And as we zoom into the Milky Way, so closer to our the solar neighborhood, what we find is traditionally we know that the sun is inside something called the local bubble. But if we look at this information, so this is the inner 300 parsecs, and we think the local bubble is roughly about 100 to about 150 parsecs in width. What we find is that there is still structure inside the local bubble. So we normally treat it as a completely void region with no structure in it. But we do actually find structure inside this region. Bear in mind that this is very low density, so it's a very small sort of filamentary structure, but it is still there. So it's important to take into account this sort of structure when we're using extinction measurements in this area as well. So you can't treat it as zero, basically. And this all sort of led to this work that I'm very excited about recently, working with Lacey Buckhart at Flatiron and Rutgers on this newly discovered molecular cloud which we've called EOS. So this is one of those stories that really fell into place, like some really nice puzzle pieces, which is why I've been very excited about it. It started with this figure. So Blakesley came to me and asked, what do I think about this structure? And I've stared at galactic maps enough. I know every single molecular cloud. Now I can name them. You point to a structure, I can name it. So then she came about with this UV map, basically. So this thin sphere data. And she asked, what do you think about this? It was this huge high latitude structure that I had no idea about. And I didn't expect to see at all. So I was very curious about this. So we started digging into it a lot more. We looked at it then in the H2 intensity to total UV ratio. So that gave us a much better boundary for the cloud. And we can see it's a really huge cloud. It's spanning sort of tens of degrees across in sky at high latitude. This is where we thought everything was going to be really cool with this cloud, because when we looked at the CO, it's completely void of CO. So we have this tiny little nugget of CO here, if you can see it. But the distance to this nugget could be anywhere from like 300 parsecs away to 50 parsecs near us. So we can't place it in this cloud. So it's a completely CO dark cloud. And then we looked at it in a couple of other spaces. We looked at it in H1, and we found that it's completely diffuse in H1. So it's formed of molecular gas, not atomic. We looked at the X-ray data on the right, and it really carves out this beautiful gap in the X-ray absorption, which means we know it's a foreground structure and not a background structure. So it should be very nearby. Then we looked at the Planck data and dust column density. Again, we see this structure very beautifully in Planck in the dust column density. And it started getting a lot more interesting when we started looking at the polarization in Planck, because when you look at the cloud, I'm not sure it's very clear in this screen, but when you look at the cloud, what you see is the magnetic field is very nicely ordered along the filaments of the cloud, and it's completely disordered outside it. So all of this is nice and ordered, and all of this is disordered. And it's really fascinating because the tiny area where we expect the CO nugget to be is slightly inclined as well in the magnetic field ordering. And then what I did was, okay, we have some of these structures. Where is this cloud? So this is where distribution came in. I had already mapped this region in 3D. So this is the integrated map for the cloud. And we can see again very nicely the same structure that we saw in UV that shows up very nicely in the integrated extinction. But then we can look at this cloud in 3D. We can place its position. We can actually figure out what its shape and size is. So with distribution, we were able to say, okay, it starts at about 94 parsecs and goes all the way out to about 136 parsecs. So it's sort of this flat, elongated structure. And it's about 35 parsecs by 52 by 45 parsecs in real size. And on sky, it's actually one of the largest single structures that if we could see in the UV, that we would see. And it's, for context, is about 45 moons across. So we wanted to look at, okay, what might be causing this UV emission? What might be causing this UV excitation for this cloud to show up like this? So we looked at it in context of the local bubble. So there's a few local bubble models here. So I've applied two. The one in green is the one that we agree with very well, which I believe is the O'Neill local bubble model. And the one in blue is the Pelgrim's local bubble model. So what we think is happening, and this is our cloud here, and this is the North Polar Spur. So what we think is happening is that the interaction with the local bubble and the North Polar Spur is basically causing X-ray excitation of the Eos cloud, which is why we can actually see it in the UV now. So I normally do this interactively, but I don't want to switch screens or anything like that. But this is normally what we look at when we look at the local bubble and the dust structure. So there's a sort of density scales that we look at. And we expect Eos to stay here. But we don't see it at all because it's quite a diffuse cloud. So this is how we missed it for all this time. So in the bottom panel is where I've basically saturated the density scale. And now we can see it very nicely. So this is a little cloud here. And everything else is just saturated material that we have from distribution. So we were also able to measure the mass for the Eos cloud because we actually have its proper structure now. And nearly done. So we were able to get the mass for it. And what we can basically tell with this mass is this could be evidence because theory has suggested for a long time that there's a large mass of CO dark gas and that there's a lot of missing mass for star formation that we haven't found yet. So the Eos cloud is very likely evidence for this missing mass. And so this has sort of now led to this mission that Erica Hamden is leading at the University of Arizona called the EOS mission, which is what we named the cloud after, to actually map all the galactic molecular clouds in industrial scale in UV to be able to try and detect all this missing gas and be able to have a better consensus of how much material is available for star formation in the local universe. And yeah, with that, I'll leave this really cool animation that a collaborator of mine helped make up and take any questions.
If you don't mind, could you show us what the interactive thing is?
Oh my gosh.
Maybe repeat the question.
Yeah, so can I show what the interactive versions look like? So yeah, so that's sort of, yeah. So it's publicly available. You can just go play with it. I always keep on doing it. Sorry.
What is your best estimate distance?
Distance from the sun. Oh, I never mentioned that, 94 parsecs. And we checked another dust map. So the Edenhofer dust map puts it at 90 parsecs. It's slightly closer, actually. So it is the nearest molecular cloud to us.
I see three questions, but we can have two quick questions.
Oh, that was really cool. Do you think you're going to be able to find more clouds this way?
This is exactly the plan, yeah, especially with the EOS mission. And we want to look more into the film sphere data because we can see a lot of these large structures that we haven't really seen before.
The star formation activity in that cloud.
I purposely skipped this slide out actually because unfortunately we think EOS is dissipating, not star forming, which is very sad. But
We can have only last question.
Do you know the volume density in like particle per cubic centimeter units?
oh gosh, not off the top of my head, but I can look it up for you. Yeah.
With such a diffuse cloud, it may not be.
Yeah, exactly. So with EOS, we think it's in disequilibrium, it's diffusing, it's not star forming, it's not a frequency of star forming cloud yet.
Okay, we should move ahead, and if you have more questions, you're welcome to discuss with the speaker. Our next speaker is Jim, and he will talk about dust evolution with redshift.
Do I have that mic actually? Sure. All right, thank you. All right, hey y'all, my name is Jed McKinney. I'm a Hubble Fellow now at UT Austin. I'm going to take us a little bit outside of the Milky Way. I really care about dust sort of across cosmic time, you know, in our backyard for sure, but out to like sort of the early baby steps of galaxy evolution and formation. I'm going to be taking this opportunity to talk about a question that I've been totally obsessed with for the past year, which is does dust evolve with redshift? I think this topic is actually well suited for a conference like this, where we have people from lots of different areas, because dust is something that, you know, it's in a lot of our observations, but it's playing a really fundamental role in astrophysics at a really wide variety of scales. Okay, but what is dust? So when I talk about dust, I'm referring to these sort of angstrom to micron scale conglomerates, mostly carbon with maybe a little bit of silicon, but you know, just have this sort of type of particle in the back of your head. And I really care about dust because it turns out that it's absolutely critical for setting the ways that we have to observe and also interpret most of the formation of mass over the history of the universe. So this is sort of a prototypical plot in galaxy evolution. Is showing the volume average formation rate of stars as a function of cosmic time. And you can make this measurement both in the infrared And say in the optical, and those are reciprocally or respectively tracing dust obscured versus unobscured star formation. And as you can see from this orange curve, for most of cosmic time, stars are forming deeply embedded within clouds of dust. Okay, cool. So you have to go measure that in the infrared to get the most precise measure. But we really don't know much about sort of the dawn of dust and sort of pushing that out to early. That's a really interesting and actively growing area. And we're starting to find dust so early in the universe that it's not necessarily coming from AGB stars. It's probably forming from supernova ejecta. It's accumulating much, much quicker than we thought possible. There's a big problem where even though that's the case, we're still assuming that that dust is fundamentally the same as, say, what we observe in the Milky Way. And I'm not quite sure that that's the same assumption. So we're at a cool time where we can kind of revisit some of these core assumptions in our field. It's also extra important for the growth of supermassive black holes. So this is a similar plot to what I just showed you. It's the growth rate, the volume average growth rate of supermassive black holes over time. And as you can see, black holes, supermassive black holes of the center of galaxies are overwhelmingly growing, hidden, deeply obscured by dust. And similarly, we're really starting to learn a lot more about sort of the dawn of dust and how important it is for the growth of supermassive black holes, populations like little red dots, and also radiolab AGN at redshift greater than 7 that JWST has really been helping us understand and find for the first time, are helping us better understand sort of this early picture of galaxy formation. Okay, so dust is super important in the formation of stars and in the growth of supermassive black holes, but it's also it's playing a really important and fundamental role in astrophysics at many, many scales. And I just want to hop through these really quickly to convince you that dust is like maybe one of the most important things in galaxies. So we know first and foremost that dust attenuates light, right? And it must be corrected for at shorter wavelengths to derive, say, an accurate stellar mass of the galaxy. So it's a fundamental ingredient in this recipe for things like SSP models, right? If you want to build the SED of the galaxy. Okay, so we have to correct for it there. But dust is also heating gas and setting the thermal structure of the interstellar medium. This is sort of an elementary plot that I'm showing here, showing various heating and cooling rates at play in the IXM. What I've highlighted in red and what is dominant over a wide range of densities is the photoelectric heating effect from small dust grains. And this is absolutely critical for, if you want to pen and paper derive the two-phase model of the IXM and the Milky Way, for instance. Dust grains also catalyze H2 formation, and H2 is, of course, a key ingredient to form stars. That actually happens on the surfaces of dust grains, and the efficiency of that process is highly dependent on the grain properties themselves. If you have water or carbon dioxide ices, for instance, that can make these grains stickier and really help promote the formation of H2 in dense gas. And then finally, this is very much not my area, but super cool. This is a simulation by Machine Newton showing that when you change the dust grain size distribution, you get out different planetesimal seeds. So that's the difference between these three panels. It's sort of the exact same initial conditions. All they've done is seeded a planet-forming disk with different size dust grains. And as you turn that knob, you start to produce drastically different planetesimals. Okay, so dust is playing a really fundamental role on AU scales all the way up to kiloparsec scales. It's this really important molecule that is, less than 1% of the mass of the galaxy, but profoundly shaping how we interpret observations of these galaxies, but also all the interesting physics that's sort of wrapped up within them. And so I think that leads to a question like this: are the properties of dust the same at all cosmic times and in all galaxies? And if not, how is that shaping this trend of dust obscured star formation and the growth of supermassive black holes, over the last 13 billion years? And that's where a lot of my research takes place. Before I get to what I do in the infrared, I just wanted to preface some evidence from optical. These are indirect observations of dust. And what we know just from our backyard is that there are canonical variations in the attenuation law, in the LMC and the SMC across various sightlines in the Milky Way. These are all attributed to different dust grain properties. This is a really interesting work from Alice Shapley showing the monochromatic attenuation for galaxies at redshift 0 and also at redshift 2 statistically. And basically, those all kind of fall along the same part of this plot. But in order to make that happen, we know that the dust surface densities are increasing at high redshift, which in order to reproduce this, you would have to lower the dust mass absorption coefficient, which again changes the dust properties, which could profoundly impact, the role that those dust grains are playing in the interstellar medium, related to star formation, et cetera. And then finally, I just wanted to highlight some work by Olivia Cooper, a graduate student at UT Austin who I work with, and she's really pioneering some empirical methods to measure the attenuation law in some of the most massive and dust-obscured galaxies at high redshift, where we've never really been able to directly probe those attenuation laws before. And she's doing with near-spec spectroscopy to measure passion lines, and again, finding slight differences with what we're kind of used to given like Milky Way. So this sort of indirect evidence, predominantly based on the optical, that dust can be very different at high redshifts and spec. Now I'm mostly an infrared observational astronomer. I work mostly in the infrared, and that's because this is sort of like a gold mine for studying dust, right? So you have all your thermal continuum emission from cold to hot dust, ambiently heated, say, by stars or supermassive black holes. But I want to talk to you today about some of the work that I'm doing with spectroscopy in the mid-infrared. This is really the gold standard because it lets you go in and directly measure the properties of dust grains, which is super cool. You can actually ask, are these grains 10 billion years ago similar or different to what we see, say, in Milky Way? Okay, and this is the type of data that I work with. This is sort of a classic mid-infrared spectra. This is courtesy of Thomas Lai, who's over at IPAC. This is a local luminous infrared galaxy. And what you can do with a mid-infrared spectrum and all the features in here is, well, you can measure the isopacity, which is ice frozen onto the surfaces of these grains. You can look at this 3.3 micron pod, which is a diagnostic on the abundance of your smallest particles. You can look at these longer wavelength pods, which tell you about the larger pods, but also the neutrality of your population. And then finally, you can look at the silicate feature at 9.7 microns to get the silicate abundance in your grains as well. So these are all really powerful diagnostics that basically we've been using Spitzer and archival Spitzer data to study for years, and now JWST is here and has sort of reopened this window and done so in an enormously powerful and precise way. And so in cycle 2, I was awarded about 40 hours on the telescope to do near LRS slit spectra to sort of fill in this wavelength gap between 5 and 14 micron in redshift 2 galaxies to enable these direct dust grain diagnostics about 10 billion years ago. And we're doing it with really exquisite precision. So here you can see in the top left corner, we have our TA images, which are like 45-second exposures that we use to place the slits. We have these really nice 2D spectra that we're using to extract the 1Ds and stitch those together with the Spitzer data to get a complete 5 to 30-ish micron spectrum and really unpack a lot of these dust grain diagnostics at early points. And I think what we're learning really is that the dust properties are not the same. We see significant variations. And I don't have time to really get into what those are, but it has to do with the isopacity features and the strength of some of these small grain points as well. And with a sample as large as this, I'm showing you about a third here, we can span both redshift and the relative strength of the active galactic nucleus to the star formation rate of the galaxy to see what are the important knobs that are changing the dust grains that we're seeing in these galaxies. Okay, so I think I'm here to claim that dust is really not the same in all galaxies and at all cosmic times, and that this is something we should be concerned about, again, because of the profound role that dust is playing in shaping the formation of stars and the growth of supermassive black holes. So if that's the case, then we need really good representative samples of galaxies, of dusty galaxies, to kind of study the impact that the grains are playing on the formation of stars and black holes. And I've been working mostly in the Cosmos Web field to do that. I'm showing that here. This is the largest extragalactic field taken in cycle 1 of JWST. And it's really just, this is an exquisite map. I mean, you can keep zooming in and zooming in and see more and more galaxies. So this is a really, really rich field, which is exquisitely well suited to studying, as many dusty galaxies as you might want. That's exactly what I'm doing. I was awarded some cycle 3 time through an archival proposal, basically to mine this field and use ALMA and JWST to uncover as many obscure sources as we could. We use that to find one of the highest redshift submillimeter galaxies to date. That was in collaboration with Sinclair Manning, a former Hubble fellow, now at UMass. And we just put a paper on ARPAD that's matched JWST and ALMA observations to about half of the sample, so millimeter galaxies of the cosmos. So we're really building one of the largest and most complete samples of dust obscured galaxies that's helping us push out to Redshift 6 and beyond. I don't have time to get into all the results of this paper. I encourage you to come talk to me about it. I'm super excited about it. But leveraging both the sensitivity and the resolution of JWST and the sheer size of Cosmos Web, which is really an exquisite data set, we're finding some really cool things. For instance, we're uncovering stellar bars that are growing in highly dust obscured galaxies. Really never been able to see those before in sub-millimeter galaxies because we've never had a telescope that's sensitive enough and has that spatial resolution to punch through those high AVs. We're putting the most precise estimate on the abundance of these galaxies out to Redshift 6, and we're also finding that they're significantly more clustered. So these are really signposts for the cosmic web. So if you're interested in studying clustering, I would say dusty galaxies are a great place to start. And I'm out of time. Okay, so I'm going to leave my summary up and just kind of have this one last comment, which is that I'm really enthusiastic about dust. I've worked sort of on its properties in the Milky Way all the way out to high redshift galaxies, and I'd love to work with you if you're just broadly interested in it as well for whatever your problems are. So happy to take any questions. Thanks for listening.
Any question?
So this is super interesting. As a supernova person, but someone who doesn't work on dust, how certain, well, not certain, but how much should we try to understand about supernovae in our local galaxy and local environment in terms of understanding their dust properties and dust formation that can then inform you? Because I think that the dustiest supernovae that we're finding are those that are interacting with quite a bit of material, indicating that their genitor stars were quite enhanced in terms of the mass hospital explosion. Maybe that works very well, but that has to point towards a certain population of stars in the early universe that would give you that much material.
Yeah, absolutely. So the question was about supernova yields and what we can do in the Milky Way to better understand the amount of dust that we're finding.
Extragalactic gas.
Yeah. So this plot right is showing the volume density of dusty galaxies at early times, and if you were to go and measure the mass in some of these galaxies out past Redshift 6, it would be quite a lot. And as you start to even step a little further in cosmos, it's just not possible to make that amount of dust with an AGB star. And so I think if we could really nail down dust yields from supernova, that's the most helpful thing, because then there's going to be profound differences, right, in sort of like pop 3 stars and like what those are really yielding. But if we can at least have some sensible prior from the type of like supernova in our backyard, I think that'd be enormously helpful. And also the characterizing the properties that are coming out of those supernova, because this is the thing, I'm pretty sure that the grains themselves are actually different than what you get in an AGB yield. So the total dust grain size distribution is shifted. And so that's profoundly changing your attenuation law. So you want to get an accurate stellar mass, you better make sure your attenuation law is right. But also it's changing all your photoelectric coupling. So I think there's tons of areas to kind of study supernova dust in detail in the Milky Way to better understand some of these galaxies.
I think we are behind our schedule, so you may want to discuss more after the conference.
Thanks, y'all.
Okay, our next speaker is Raphael Scalini.
Hello everyone, I'm Raphael Scalidis and I'm a fellow here. My presentation focuses on the estimation of magnetic field strength. So why do we care about magnetic fields? And the answer is simple, because they are everywhere. And here you can see a projection of our galaxy where the column bar shows the total dust column, and the beautiful drapery pattern shows the plane of the sky magnetic field morphology as traced by data from the Planck satellite. And you can see that magnetic fields are everywhere, so we cannot ignore them. And second, if you consider the various energy components in the interstellar medium, magnetic fields are roughly as important as anything else. So if we want to understand this energy balance in any reasonable detail, we need high precision estimates of the magnetic field strength. Point on hand, in star formation, there is a raging debate about the relative importance of magnetic fields. In brief, if magnetic forces are strong enough, they can support a cloud against its self-gravity. And so clouds are magnetically supported and they cannot form stars. The relative ratio between gravitational forces and magnetic forces is the mass flux ratio and is expressed by denoted here with this new symbol. And it quantifies the relative importance of magnetic fields. So when this ratio is smaller than 1, clouds are magnetically supported, and this corresponds to subcritical clouds. And you can see this region here in blue. When this ratio is larger than 1, then clouds can collapse, and magnetic fields are considered as dynamically unimportant. So the figure here shows mass flux ratio of several nearby clouds as a function of the equal densities. And you can see that the vast majority of the points are clustered around this critical value for collapse. And this is a major challenge because we need to understand whether these points are above or below these lines to assess the role of magnetic fields. And in order to do that, we need high precision estimates of the magnetic field strength. So there are not many observables. Actually, there's only one observable that we can use to measure magnetic field strengths. And this can be done through the Zeeman effect. But unfortunately, Zeeman data are noisy, and so we cannot rely on them. And traditionally, the community has relied on alternative approaches. And dust polarization is one of the most widely applied methods for tracing magnetic properties in the ISM. So dust polarization arises due to the interaction between of spherical grains and magnetic fields, and it probes the plane of the sky morphology of the magnetic field. And we observe dust polarization in optical wavelengths and submillimeter wavelengths. And here you see some examples of dust polarization maps of 4 nearby molecular clouds, where the color bar shows the total dust column, and the daily pattern again shows the morphology of magnetic fields in the plane of the sky. And you can see that in this data set, we can constrain the morphology of these clouds very well, but not the strength. However, if we are creative, we can find some ways to constrain the magnetic strength from these maps. So the main idea goes back to the 50s, when Davis and independently from Rascal and Fermi developed a method to estimate the magnetic strength of dust polarization maps. For convenience, I will refer to this method as DCF. The idea is the following. Consider a cloud permeated by a magnetic field that is uniform. Then the observed polarization map will look uniform to us, shown here on the left. And now consider that we have some perturbations. Then the observed polarization angle map will become dispersed, as shown on the right. And the larger the dispersions, the larger the perturbations, the larger the dispersion of polarization angle map. Mathematically, this DCF method, it can be expressed in this form, which is shown here, which connects magnetic field strength with the gas volume density, the gas velocity, and in the denominator we have the dispersion in both the polarization angles. And you can see that if we increase delta theta, then B0 increases. However, it was soon realized that the method tends to overestimate the magnetic field strength significantly, and for this reason, several modifications have been proposed to correct for different biases. But the major problem is still there. The method assumes that perturbations propagate in the form of Alben waves, which are incompressible. But the ISM, molecular clouds, are highly compressible. So there is an inconsistency. So skipping a few steps, we relax this approximation and we derive a new formula that takes into account the compressible modes in the estimation of the magnetic strength. So let's proceed and explore the difference between the two methods. So first of all, you can see that there is a difference in the scaling. Here, delta theta has a linear scaling, while here it has a non-linear scaling. So we can express the difference in the scaling as a function of the algebraic Mach number, which is a metric of the magnetization level of Einstein turbulence. So we constructed synthetic data correlating to numerical simulations to test the scaling. And the figure here shows the dispersion polarization angles as a function of the algebraic Mach number. The black dots correspond to the synthetic data. The magenta line shows the previous scaling, the linear scaling of the DCF method, while the blue line shows the new scaling that we derive when we take into account the comparison modes. And you can see that the previous scaling fails with the data, while the new scaling is consistent with the data. But the actual question is, can we improve the estimates? Can we get higher precision in the estimates with a new method? To answer this question, we applied both methods to the synthetic data and estimated the magnetic strength value and calculated the differences with the actual value of the simulation. So this relative difference or relative error is shown here with this epsilon. And the figure here shows in the vertical axis the relative error of the previous method, while in the horizontal axis you can see the relative errors of the new method. The color points correspond to the different measurements that we obtained for different algebraic Mach numbers. And you can see that here in the vertical axis, the errors can go up to 3,000%, which implies more than a factor of 10 overestimation of the magnetic strength value of the actual value when we employ the previous method, the DCF method. While in the horizontal axis, the errors remain below 50% for every case of the study. And this implies that with a new method, we can constrain, we can estimate the magnetic strength and microstress better than factor of 2. So all the results so far are based on numerical data. What about our observations? Palau and collaborators targeted collapsing cores, and they constrained the mass flux ratios of this course using both methods, both the DCF method and the new method that we propose. And the figure here shows the summary of the results. So you can see the mass flux ratios as a function of the gas volume base. The green points show the constraints based on the DCF method, while blue points show the constraints based on the method that we propose. And you can see that the green points are all over the place, which implies that these cores can be magnetically supported or not with equal probabilities. But this is absurd because we know by other means that these cores are collapsing. On the other hand, with the new method, they always obtain with high probability that the cores cannot be magnetically supported, which self-consistently fits with the picture that we have for this course. So now, in the last few minutes, you can see the slide. In the last few minutes, I would like to discuss, I would like to present our new, the next steps, what we can do with these kind of tools. And I would like to introduce the Pacify experiment. Pacify is an optopolarimetric survey that is going to run from both hemispheres. And Pacify will obtain millions of polarization measurements at high galactic latitudes. And the goal is to combine these polarization measurements with guide distances to constrain the 3D morphology of the ISM. And while our major instrument is being constructed, we performed a pilot survey where we targeted a small region, almost 4 square degrees, and obtained almost 2,000 polarization measurements within this small region, and applied our tomographic algorithms in order to see how the magnetic field fluctuates along the line of sight. And here you can see this white color here corresponds to the individual polarization segments that we obtained, So these are actual data, and this shows the line of sight of the target. And now we move along this line of sight, and you can see, hopefully you can see the various clouds, and the drapery pattern shows the magnetic field morphology that we inferred for these clouds. So you can see here, as we move along the line of sight, we have we detected several clouds with different magnetic field morphologies. So we are able to get a 3D reconstruction of the morphology of the magnetic field in this region. So with this data set and this pipeline and the new methodology that I presented today, we can obtain a realistic 3D models. We can build realistic 3D models of the galactic magnetic field, including both the morphology and the strength of the field. So I would like to thank you all for your attention. Any questions? Okay.
Extremely fascinating. So you said that your survey is going to be focused on the high and low latitude sort of clouds or regions in the Milky Way. What sort of cloud, I guess, like parameters or sort of types are you going to be seeing at these high and low latitudes? Do you have any counterparts that you've already found in that along that line of sight that you can detect in other? Can you say what's the formula or anything like that?
So these are mainly diffuse H1 stars, right? And sometimes we can, if we go a little bit low, right? We are targeting molecular clouds, but not very dense clouds, right? So these are, diffuse molecular, usually non-star forming clouds.
So when you do these reconstructions, are you using any fire where you know the dust is from other sort of dust?
Yes, actually, yeah, we can definitely benefit from 3D dust distinction maps like the ones that we presented before. And also H1 data. All of these priors are very useful for this. But we don't necessarily need to include all this information always, but this is definitely very helpful.
Okay, last question, Jeff.
Super cool talk. So you're trying to measure the dispersion of the angle of the magnetic field. That's an important part of this observation. If I recall correctly, that's also a function of the dust grains themselves, right? Because if they're more or less like prolate or they're like more sterile,
yes,
you can start to muddy up that signal. So are you concerned about?
Yes, yeah, that's a good point. The good news is that we can identify those cases because if grains are spherical and not very asymmetric, then they do not induce any polarization. So the degree of polarization will be very low and essentially we don't get any signal there. So we can distinguish, we are observationally biased in regions where there are spherical grains. Okay, thank you very much.
Thanks for and she will talk about cosmic ray scattering.
Thank you. Hello, everyone. My name is Irina Butsky. I'm a Hubble Fellow at Stanford, and before that, I was a postdoc here at Caltech. I'm excited to talk to you about my work with cosmic rays. So before we get too far into it, I just wanted to define what I mean when I say cosmic rays. So we probably all know that cosmic rays are relativistic charged particles, and for some of you, they may also be a big headache when it comes to your observations. I'm sorry for that. But when I talk about cosmic rays, I'm talking primarily about GeV energy protons, which make up, the majority of the cosmic ray pressure in our interstellar medium. And to put up an even more simplified version of the pie chart from Raphael's talk, they're roughly in a condition with the thermal and kinetic energy in the ISM. And this is perhaps surprising because if you just look at the number of particles, cosmic rays make up about 1 in a billion particles. But their coupling with magnetic fields makes them an important part of the energy budget in the ISM. And so even though cosmic rays, the individual particles move at close to the speed of light, they don't just escape the galaxy after being accelerated in some very short amount of time. They are actually confined to the galaxy for about 30 million years or so because of the way they interact with magnetic fields. So because they're charged, the cosmic rays have to go around the tangled galactic magnetic fields. And galactic magnetic fields aren't just tangled on large scales, they have lots of features on small scales too. And when I say small scales, I mean roughly the size of the cosmic ray gyro radius, which is about 0.1 AU for a GeV proton. And so these small perturbations in magnetic fields will scatter the pitch angle of the cosmic ray, which is really forcing the cosmic ray to do kind of a random walk with momentum along the magnetic field line, which on large scales looks like a fluid diffusing. And so this is great news for us because then we can not have to model each individual cosmic ray particle when we're simulating a galaxy or a molecular cloud or planetary disk. We can use our fluid equations with some transport parameter. And so in the spherical cow model of cosmic rays in the galaxy, kind of the rough picture that happens is supernovae inject about 10% of their energy into accelerating cosmic rays. This cosmic ray fluid then diffuses outward down its pressure gradient, and it sets up a pressure gradient that can counteract gravity and drive pretty significant outflows. And so my kind of path into studying cosmic rays actually came from studying circumgalactic media. And the coolest, I think, result in the last decade or so of people studying galaxies and the CGM with cosmic rays is the formation of this cosmic ray pressure supported inner CGM around low redshift Milky Way mass galaxies. And this happens in a variety of different codes, in different groups, with within some reasonable range of cosmic ray transport parameters. And the details here don't matter too much, but all of the visually you can see all of these panels have this inner kind of circle or spherical region that is primarily supported by cosmic ray pressure. And that region behaves very differently from a thermally pressure supported CGM that we all have our physics intuition built around. Cold gas is going to be a small dense lump that's going to fall into a gravitational potential. But when you have so much cosmic ray pressure, you instead get these really large, low density gas blobs that hover in the atmosphere, and that affects accretion rates. It affects outflows. It affects a lot about our assumptions of the circumgalactic medium. And the funny thing is that we don't have enough information both from theory or from observations to be able to tell between a picture of this wacky cosmic ray pressure supported CGM and one that is primarily supported by thermal pressure. And the problem is that our models of cosmic ray transport are extremely under-constrained. And this is because all of our observations from which we derive the cosmic ray transport models come from observations either very, very close to the Earth or at best, the Milky Way interstellar medium. And then what we're doing is we're taking those transport models and trying to apply them. We're trying to apply them into the circumgalactic medium or maybe in the interstellar medium of other types of galaxies. And if you don't understand the underlying physics that's driving this average cosmic ray scattering, then you can run into some serious deviations depending on what models you assume. And so in the past several years, I've been trying to constrain cosmic ray transport with two categories of approach. One has been by directly trying to place constraints on the cosmic ray transport rate in the CGM. And so we actually with Sam sitting there in back, came up with this toy model for estimating the lower limit of the cosmic ray diffusivity, add some impact parameter with three theoretically observable properties. So the time at which star formation rate, the circular velocity at some impact parameter, and the total hydrogen column density. And it's that last one that's the trickiest, as I'm sure many of you know, because any one observation is really only sensitive to some subset of like phase of gas. So you do have to make some assumptions. Do you want to measure the total or estimate the total hydrogen column density? But those error bars are nowhere near as bad as the error bars we have on the cosmic ray transport rate. So if you have some way of estimating the total hydrogen column density in the halo galaxies, please come talk to me. So we applied this to the COS Halos data set, which very conveniently published their estimates, even though they have very large error bars. Those error bars you see on there are basically entirely due to the estimate of the total hydrogen column density. And so this is a sample of L-star galaxies around a redshift of 0.2. And what you're looking at is the estimate of the lower limit of the cosmic ray diffusivity as a function of distance from the galaxy center, normalized by the real radius of those galaxies. And this is exciting because this is essentially the first constraint of cosmic ray transport out in the CGM. So what this is telling us is this gray shaded line is roughly the transport rate in our interstellar medium. And if we assume that other nearby Milky Way massive galaxies should have similar transport rates in their ISM, this plot is really hinting at the fact that in the outer CGM, we expect cosmic ray transport rates to increase, which essentially rules out any models that don't predict that increase in the cosmic ray transport rate. But there's still a lot of work to be done, especially looking at galaxies at different masses or higher redshifts. Okay. The other way of thinking about constraining cosmic ray transport is by going back to our observations of the interstellar medium and thinking about the theories of what is causing cosmic ray scattering, so that if we have a robust theory for what is causing cosmic ray scattering in the ISM, we can be much more sure about how we apply it to other environments. And one of the biggest results in the last few years has been that traditional scattering models, or like our traditional theories, are fundamentally flawed because they all hinge on this assumption that cosmic rays are scattered or are very slightly scattered throughout the entire volume of the ISM. And so then the picture is that you have some, the black line is magnetic fields, and so I have, you have your larger perturbations that scatter the higher energy cosmic rays and smaller perturbations that scatter the lower energy cosmic rays. But if you start with this continuous scattering assumption, then in order to reproduce the energy dependence of cosmic ray scattering, that strictly imposes this very specific energy scaling of these perturbations in the magnetic field, which the theories don't reproduce for a variety of reasons. And so together with Phil Hopkins' group here at Caltech, we've been working on an intermittent model of cosmic ray scattering that says, okay, well, let's say that instead of being continuously scattered just a little bit, so these cosmic rays are free streaming most of the time, and then every once in a while they encounter some scattering structure that strongly scatters these cosmic rays. And in this model, we can have large structures scatter both high energy and low energy cosmic rays, and smaller structures only scattering lower energy cosmic rays. And so by having a distribution of sizes of these hypothetical structures, you can completely sidestep this problem of requiring a certain spectrum of magnetic field fluctuations while still reproducing all of the relevant observations. And so we recently published this paper, kind of like walking through this toy model, coming up with what would the sizes of these structures need to be, the volume filling factors, area, et cetera, et cetera. And so this is a plot showing the volume filling fraction of these hypothetical scattering structures as a function of their size. And what you don't see on here is that basically all the macroscopic structures in the interstellar medium are almost immediately rolled out. You know, stars, stellar magnetospheres, general electron clouds, phase structure of the ISM. But a lot of microscale structure in the ISM still actually can very well explain this cosmic ray scattering. And in particular, so what we need to scatter, say, a GeV cosmic ray is some structure that has a mean free path of about 10 parsecs and a size of about 0.1 AU. And this is eerily similar to the substructure that's been observed in the ISM for decades. That we're getting more and more data on now. We should check out how stellar hoppers work here out there. And also on the theory side, we now have these really high resolution simulations of energy turbulence that show the formation of these magnetic islands or plasmoids that also have very similar properties and can scatter cosmic rays. So I think we're actually, now that I'm out of time, I think we're so close to figuring out cosmic ray scattering, and stay tuned for that. Thank you.
Any questions? Okay, actually, I have questions. Like you mentioned the plasmoid. I wonder what's the volume filling factor of it? Can it scatter cosmic ray effectively?
Great question. I think there's still a little bit more work to be done to figure out like exactly what the volume filling factor of those are, but so far it does seem like it can be consistent with that. And there's also separate work showing that like these kind of curvatures in the magnetic field can effectively scatter cosmic rays.
Okay. And the second question, you mentioned also the mean free path of cosmic ray is around 10 parsec. You mentioned that you need something to scatter it. I wonder if you consider turbulence, because turbulence in ISM, the injection scale is 100 parsec around. So at 10 parsec, turbulence is still significant. Maybe it can be one factor.
Yeah, so actually one of the traditional theories kind of assumes that it's the turbulent cascade. Yeah. There are several problems with that because, first of all, the scales at which you need to scatter the cosmic rays are like well below the dissipation scale. I think the injection scale of turbulence there might be something related to that, but I think again, what you would need is this feature that's very kind of discontinuous, that can very significantly scatter a cosmic ray that's also on this very small scale. So okay. I guess TBD.
Okay. Thanks for a very nice talk. And our next speaker is. Okay, our next speaker is Andre, and he'll talk about the 3D dust map.
All right, hi everyone. Thanks for having me. It's been great meeting you all over the course of the last few days. My name is Andrew Sadri, and I just graduated with my PhD from Harvard, and now I'm a first-year Hubble Fellow at Princeton. And my work really focuses on trying to understand dust in the interstellar medium, where it is, how it's moving, and what it's made of. And today I'll be telling you about my work towards the first of those thrusts of my program, about how we made the highest angular resolution 3D dust map. So as Hubble Fellows, we're supposed to be answering the question, how did we get here? And I'd like to take a step back and ask an even simpler question of where even is here, okay? We are at the center of this 3D dust map. It's the question this 3D dust map is trying to answer. It has exquisite Cartesian galactic coordinate resolution out to around 1.25 kiloparsecs. Other 3D dust maps, like the Space Star 19 map that I'm now zooming through here, reaches out to much larger distances, around 10 kiloparsecs. As you look down on the top of the plane, you can see there's about a third of the plane that's missing here. And so the talk that I'll be giving today will tell you how we filled in that third of the plane that was missing, and how we pushed both photometric extraction methods and 3D dust mapping methods to really take full advantage of the information that we have in our data to make the highest angular resolution 3D dust map. Okay, so a brief overview of how 3D dust mapping works. We have a telescope that measures some stars. There's some dust clouds in between us and those stars. And we measure the reddening of light as it arrives towards us through those clouds. And by having a large number of stars at different distances with different lines of sight probing different combinations of clouds, we can reconstruct what the distribution of those dust clouds must have been when combined with an assumption on what we think stars look like. Okay, that's how the general procedure works for extinction-based dust mapping. And before I show you our map, I want to just contextualize our work in the context of some other dust maps that you might have seen. So on the left, I'll be showing emission-based dust maps. These are slightly older. They look at just basically the hot and warm dust and how it's radiating in infrared. And maybe the most famous dust map in astronomy is based on IRAS and Derby data from about 100 microns in its wavelength. This is the so-called SFD dust map. And I'm just showing it to you on a test patch that I want to use for comparison. On the right, I'm showing you the first extinction-based dust map that I showed in my slides based on Gaia XP data. And the one thing you might note about it first is that it's not as bright as the image on the left. It's only reaching out to 1.2 kiloparsec, so it's not capturing all of the dust along the line of sight. And where it is present is at pretty low angular resolution in this bottom left-hand corner here. And that's a trade-off that most people have to make to get the high Cartesian resolution. So other 3D dust maps, like the second one I showed you, based on 19, go to much higher angular resolution, like that shown on the right, starting to see substructures that are matched to the substructures you see in this SFD map. And then after this point, I mean, emission-based dust maps kind of ran away with the game of high angular resolution. So we had missions like WISE, and just because we're here in California, I'll highlight Herschel, or Planck first. So Planck goes a little bit better. And then we have Herschel and Spire, which really shows you a very high angular resolution down to 36 arcseconds that you have filamentary structures all the way down. And you can see that this sort of structure is totally not resolved by a 3D dust map like BaseStar 19 on the right. And so I'll tell you about today is that we were able to make a dust map like the one shown here that I would argue is a very good match for the angular resolution substructures that you're seeing in the Herschel image using extinction-based dust mapping methods, using the photometry from the Deckham plane survey or DCAP survey. So one important thing to remember about extinction-based dust mapping, the method shown on the right, is that there's three-dimensional fundamentally. So I've been integrating it out to a large distance to make these comparisons, but I can play a video that shows you we can remove dust at different distances, showing you only the nearby dust, and when it's played in reverse, obviously we're building up clouds again in the other direction. And that's giving you information that just fundamentally isn't present in this Herschel image. You have no idea what these different arches and clouds are. And you can see that some of these more distant clouds that were just totally missing in BaseStar 19 are missing in part because they're distant, they're highly extincted, and the photometry just wasn't deep enough. Okay, so this is a test patch region I've been showing you. Let me just zoom out to help you contextualize the angular resolution that we have across the whole survey footprint that we have it on. This is our survey footprint. You can start to see globules getting disrupted. We're now looking at plus or minus 10 degrees off the galactic plane, and you see filamentary structure all the way down. You see famous molecular clouds, and I think this is really trying to show us that we need to go beyond the standard power spectrum approximation, the standard approximation that everything can be modeled as a Gaussian random field. I mean, this clearly has non-Gaussian structure that we need to capture statistically and model. And here in this final zoom in, I really like to show these sharp edges here that you're seeing and able to resolve that are probably dust being entrained in some sort of feedback mechanism or some sort of shock front. Okay, so all of this is based on photometry from the Deckham plane survey. What is DCAPS? Well, it's an optical and near-infrared survey of the galactic plane in 5 photometric bands, G, R, I, Z, and Y. And it was motivated by looking at a coverage map of large surveys prior to its inception, where you can see that Pan-STARRS is really just covering the north, and there's this big hole in the south. And we have some coverage at longer wavelengths in the plane by VVV and glimpse. But we set about to try to fill in that coverage in the optical and near-infrared using Deckham to plus or minus 5 degrees off the plane with DCAPS 1, and then plus or minus 10 degrees with DCAPS 2. This is about 6.5% of the sky, and it sees on average the photometric depths that you see there on the right. And it's just several magnitudes deeper than Gaia. So this is high quality, deep ground-based photometry. Okay, so one of the main benefits of the photometry from DCAPS is that we worked very, very hard to do the photometry in the crowded field limit and in the limit of the galactic plane where things always have very structured backgrounds. You have a lot of gas and dust, and so extracting the photometry is difficult. So we pushed on the methods here, and I just want to talk about this general problem of component separation to the background and with this test region, which is an H2 region and a CD116. So we can try to model just the flux of sources in that center area, just looking at the R band of that image. And the way that most photometric codes are going to do that is they're going to make some locally smooth background models, smooth on scales much larger than the point spread function, drop down some PSFs, and you'll get residuals like those shown on the right here. And so you'll see this very characteristic negative, positive, negative pattern showing that you're mismodeling the filament as it's moving into and out of your moving median filter. And you might just say, who cares? All I care about is the photometry. Who cares if I'm mismodeling the ISM? Well, you should really check that it doesn't bias your photometry. And you can check that by injecting sources of known flux and asking how you can recover them relative to your reported uncertainties. So I'm truncating this color map at plus or minus 5 sigma errors. And hopefully you can see that you are making large statistically significant errors that are exactly correlated with your residuals in your modeling of the background. And so this is showing you that you're introducing a spatially correlated bias in both your flux and your flux uncertainties that's going to poison any sort of downstream analysis that you're trying to do, especially if that downstream analysis and inference is about the ISM, right? Because this is exactly correlated with these ISM features. And so anytime I show a conventional result like this, I'm showing a photometric solution from the state-of-the-art crowdsourced photometry code called Crowdsource, which was originally developed by Eddie Schlafly, that I'm also a co-developer on. So we're really just criticizing ourselves here. And so what do you do when one of your photometric pipelines isn't sufficient? You write another one, and this time we wrote it in Julia. This is called cloudcover.jl. And the way that this works is it treats the problem as a Bayesian component separation problem, really trying to ask what is a posterior on the set of backgrounds that could have been there if our star hadn't been there blocking our observation of the ISM. And when you do that, you can think about this as a conditional background interpolation. We use techniques akin to Gaussian cross-link regression. I'm more than happy to talk about that anytime. And it allows us to get the residuals down to the plot shown on the right here, which is significantly reducing the correlation between the photometry and the filamentary structure. So we apply that to all of our detections and decaps. And how many detections is that? Well, it's actually the largest photometric catalog in terms of the number of objects. It clocks in at 3.32 billion sources built off of 34 billion detections. That's because we're doing the crowdsourced photometry very carefully. Here's just a map of the R and Z band source density for high quality sources, flashing back and forth because I want to emphasize we really like the near infrared. It allows us to reach deep into the galactic disk, which is great if you're trying to make large volume 3D dust maps. I'll just call it the fact that all the bright points you see here are known open and globular clusters, which is telling you that we are doing the deblending correctly in some of the most crowded imaging that exists, and that you don't see pointing boundaries, which is just telling you how well we're doing calibration field to field. Okay, so taking decaps as our primary target, targeting data, we can cross-match this VVV, TrueMass, Ys, and Gaia parallaxes, requiring that we detect a source in 4 photometric bands. That leads to about 800 million sources. With this distribution on the plane of the sky here, you would start to see boundaries, specifically those with the VVV survey, which does not cover our entire photometric footprint. In terms of galactocentric coordinates, you start to see that we have pretty high quality detections all the way out to around 15 kiloparsecs here away from the sun, which is at the center. I'll just note that, of course, looking at this side on, that we have a reduced density near the galactic center because of dust and crowding. Okay, so we take all of those data inputs. We then try to forward model that photometry by brute force sampling over models of what stars look like, in this case, NIST. And we do that using the Brutus package, which was originally developed by Josh Spiegel. That gives us posteriors on the distances and reddening to every star. And then we can take each line of sight, take the stars along the line of sight, and ask what monotonically increasing function best describes these posteriors. And just repeat that for every line of sight. That's what was done for the Baystar 19 dust map that I showed you at the beginning. And now we can fill in that missing third of the plane in blue here with the decaps dust map. And if I just flash back and forth briefly, you can see that in the overlapping regions, we're agreeing quite well between the two different maps, even though they're based on pretty entirely different photometry. So this gives us a complete view of dust out to 10 kiloparsecs, which is great. One top-down comparison that's nice to make is that these high angular resolution 3D dust maps are not totally optimized for top-down Cartesian projections, but we can compare them to large surveys and dust maps that are generally made based on gravity, such as the Berkeley 2022 map that reaches out to around 5 kpc. So you can see near in, maybe near in, you can see that they agree quite well. But this map based on Gaia starts to become very blurry near the edges, where Gaia's source density just falls off quite quickly. There are clearly resolving cavities and clouds beyond that. Although I will say that at the edge of every one of these 3D dust maps, you start to become dominated by distance uncertainties. Things just look smeared out. And you might ask, when things are that smeared, are we really learning anything at all? And one way to check that is to make a projection over a narrow range of distances and then just zoom that distance slice out to further and further distances and ask, do we still see coherent structure, spatially coherent structure on the sky? And the answer is yes, you do. Even at some of the largest distant places, like we see here, you see things that look like filaments in clouds. That's telling us that even if we don't know where they are at these large distances, we are still clearly resolving real dust structure. Okay, so what's next? The picture that I just showed you, we can add another dimension, which is velocity, trying to reconstruct a 4-dimensional map of the Milky Way, asking how the dust is moving. We've applied similar Bayesian component separation techniques that I talked about in the context of images to spectra and measured precise kinematics of diffuse interstellar bands with precisions comparable to those that people often talk about for CO. And so I'll be happy to tell you about that next year. So what I showed you today is the first 6 billion voxel dust map that you've ever seen. It represents an order of magnitude improvement in the angular resolution of 3D dust mapping, which really tries to answer the question of and try to better understand the spatial complexity of interstellar dust. It was only made possible by a large team of people, those doing the dead cam plane survey, doing the photometry extraction on the top, those working on the 3D dust map reconstruction on the bottom, the large cross-section of intersection between those two teams. I just also want to call out specifically Captain Zucker and Josh Siegel, who are co-leading the 3D dust mapping paper I just presented. So with that, I'll leave you with the map, and I'd be more than happy to take any questions.
Any questions? So I guess you can add more 3 dimensions by combining with Raphael's method of magnetic field.
Yeah, of course. Adding in other things like velocity and magnetic fields are great.
Yes, that would be 9 dimensional.
Question?
Yes.
So the cloud cover package is obviously a huge improvement over the other method, but it still had quite a few five sigma error bits. So is that sort of a known thing that you can tackle and get a hold of, or is that a fundamental limitation of the data?
So what most of those point sources are coming from, I'm not sure if I dare to go all the way back. I do, yeah, okay, good. So a lot of those are actually coming from blended sources where I've injected a source right on top of another source. And so there is a fundamental deblending and confusion problem, which is that if you drop a source down exactly on top of another source, you have no idea if you have 2 sources or one source of half the magnitude. So I think that's really a deblending problem that isn't something you can overcome with this. There are still some small problems related to the fact that you're doing the background modeling based on sort of the space between the stars, what you can see. So doing a full joint forward model is something that we're looking to do, but at some point you can't solve the crowding problem. So yeah, great. Yeah.
What gives you the velocity of this?
Great. No, I would love to talk about that quite a lot. So people often try to use gas, but gas and dust being assumed to be co-moving is a pretty big assumption that we also know isn't true. And so here I'm using diffuse interstellar bands, which are very broad. They're about 30 kilometers per second wide, but these small molecules that are somewhere between dust grains and small molecules are probably more co-moving with the dust. And the fact that we can now extract them with high precision means I think we have a better tracer of the dust by using diffuse interstellar bands. And we've done that on large spectroscopic surveys like Gaia RBS and also Apogee. And so we have really big, like 200,000 sort of detection samples of that.
Those are in absorption. Right?
Those are in absorption. Right. Did you hear?
Very cool. And obviously, I'm going to have so many questions for you after. I'm going to ask you a question about the dips work that you're doing and sort of demonstrate. Do you see any correlations, or if you allow for anti-correlations as well with the dust and the dips?
Anti-correlations?
Do you allow for them not to be correlated? Do you allow?
Yes, yeah. So I impose no prior that you see the dibs because you're along a line of sight that's highly extincted on some other metric. I think most people see pretty clear equivalent width of the dib correlations with 3D dust maps. But there's a lot of scatter around that relation, and I'm really interested in trying to understand if chemistry is driving that scatter, if size distribution is driving that scatter, what's driving that scatter. I have a lot of ideas about that, and that's sort of the third thrust of my research program that I'm hoping to do.
It's like there's a lot of conversation on what the dibs actually are as well.
Of course.
Okay.
Yeah.
Okay, let's thank the speaker again. And
all right, thank everybody for a great day too. I just have a couple of things before we let you go. So tonight is the dinner. And so we hope everybody who has signed up, well, everybody who's here, who has badge, that you come to the dinner. So there was a map that was sent out. It is here on campus at the Avery House courtyard. You can put Avery House into Google if you don't want to use the map that we sent out with the information for the symposium.